Hello, am I audible?
Yes, madam.
Okay. Good morning to all respected here, and good morning, Professor Kishore, who is the first speaker of this session. He has joined. Good morning to all the respected dignitaries here. Welcome to the second day of our AICT sponsored short-term training program. So before we start the session, let me read out a short profile of Professor Kishore. He was there with us in the phase one of STTP, and now he has also joined with us in phase two. So welcome, sir. Professor Kishore is presently in the Department of ECE and heading the Computer Center of NIT Warangal. And he has received his BTech in Electronics and Communication Engineering and MTech in Digital Systems and Computer Electronics from Sri Venkateshwara University and Jawaharlal Nehru Technological University in the years 1992 to 1996. He has obtained PhD in the area of signal processing in the year 2004. He has headed the Department of EC NIT Warangal during March 2015 to November 2017, and he is heading the Institute Computer Center from April 2018. He has been selected as the visiting professor for Asian Institute of Technology, Bangkok, during the previous semester, 2019, under the secondment of Indian faculty by MHRT. He was selected also for Cabinet Secretary, Prime Minister Office, and Government of India's Technical Officer. He is a member for Central Council Board, AICTE, during 2009 to 10, and member of AICTE Academy, NIT member for Central Council Board. Presently, he is a member of Andhra Pradesh State Council of Higher Education. He was also awarded with Research Excellence Award, and he has also received Best Engineering Research Award in 2017 by NIT Warangal. And he has contributed substantially to the quality of research endeavors. He has completed 2 DRDO projects worth rupees 18 lakh and 1 MHRD project. He has also done 2 projects sponsored by SERB worth 41.92 lakhs. So he has also several other projects of SERB to his credit, and he has guided about 9 PhD scholars as well as UG scholars at the UG and PG level. He has traveled across many countries like Czech Republic, France, Israel. He has organized several faculty development programs, and he has also coordinated MHRD initiated YARN course in 2016. He has delivered several prestigious lectures at DRDO, ECIL, etc. He is a member of IEEE, IST, IET, and he's a member also for Board of Studies. Presently, he is the PhD examiner for NITs and several other universities across the country. So, Professor Kishore, now you are requested to start your session. Sir, are
Yeah.
you there?
Yeah. Thank you, madam. Is it audible?
Yes, sir, you are audible.
Yeah. Thank you so much, madam, for giving my introduction. So it's very nice for your invitation again for the second time. I am coming this particular occasion. It's very nice during this pandemic situation, your institute coming forward, successfully conducting the second time of this program. Very nice, and I've seen a lot
Thank
of
you, sir.
participants also is there. Once again, I'd like to congratulate, and I'll start my session, madam. Thank you, madam.
Welcome, sir.
Please tell me, madam, my PPT whether it is coming or not.
Okay, sir.
Is it visible, madam?
Not yet, sir. Yes, sir. Now it's coming.
Yeah. Is it visible, madam?
It's still coming.
Yeah, yeah. Is it okay, madam?
Okay, sir.
Okay.
Please go
Good
ahead.
morning. Good morning, everybody. So today, last time I gave a talk on hardware software co-design for embedded systems. Now I thought that this time I want to give a introduction and applications of embedded systems. In fact, this will cover the entire concepts of the embedded systems, not only the introduction, but also my talk, it will cover the basic idea about embedded system, then what are the classifications of embedded system, then what are the different components of embedded system, then how to design an embedded system, then what are the types of embedded system, a simple two examples I'll try to give, and what are the challenges in embedded system that we have in the present day, that I'll try to discuss. This is my agenda for today's talk. Let me start the introduction with the system definition. So normally a system we will call a way of working, organizing or performing one or more tasks according to a fixed set of rules, program or plan. So it's an arrangement which consisting of different rules and regulations. Some example, when you consider a watch or automatic cloth washing machine. So these are the examples for a general system where they will work according to some organizing or performing one or two tasks according to the fixed set of rules. Coming to the embedded system. What do you mean by an embedded system? Basically, a system whose principal function is not a computational, but which is controlled by a computer embedded within it. So, the basic idea of an embedded system is if you take any engineering product which need some control to activate that particular system, or to have some, what we can say that the control over that particular system. How do I can get this particular control? By embedding some particular electronic device. So in place of an electronic device, in order to achieve this particular control, what I'll do is I will try to embed computer in that particular system. Then it is called an embedded system. There are a lot of the applications that we are observing below the figure. Let's consider a computer, where a computer is a system which consisting of different components, as you know that a microprocessor, memory, input, output. Then we have the input units. Then we have different output units. Then networking units and operating system. So basically, any common man have an idea about a computer which consisting of all these particular components. So in order to achieve the control over a particular system, I need to embed a system. I need to embed a particular computer, which consisting of all these particular components to have a control. So based on this, an embedded system, various people, they gave different directions of definitions for an embedded system. If you see these definitions quickly, I will give an overview of these particular definitions. An embedded system is a system that has a software embedded into computer hardware. An embedded system is one that has a dedicated purpose software embedded in a computer hardware, and it is a dedicated computer based system where it consisting of a software usually embeds into ROM or a flash, and it consisting of a programmable computer or a system which contains a microprocessor, or I can say that it is a microprocessor based control system. Everywhere earlier days, people used to talk a microcontroller based system is nothing but an embedded system. So how this particular definition has come into picture means here, in order to have that particular control in a computer which is embedded in place of that particular computer, people used to talk microprocessor is used or microcontroller is used. So like that, we have different types of definitions. But overall, what I can say that an embedded system which is used for a dedicated purpose. In order to achieve that particular dedicated purpose, here the dedicated purpose in the sense that we need to make our system to use for a specific application. In order to achieve that particular specific application, what I am doing is I am embedding a particular computer or an electronic device to achieve that particular application. That is about an embedded system. And basically, this embedded system, it involved different types of disciplines. So you think that embedded system is pertaining to only electronics people or only computer science people? Not like that, because when you have a nowadays, if you see, uh, I'll try to show in my slides. The 30% of the industry is based on the electronics, and most of the advanced technology depending upon various what you can say development in the different types of domains. So that's why an embedded system where which involved different types of disciplines. One is digital electronics, integrated circuit design, computer architecture, software engineering, data communications, control engineering, electric motors, sensors, and analog electronics. Like that, all these particular the disciplines are integrated together. We have an embedded system. So anybody who want to work in the embedded system, they should have the familiarity with all these particular areas. So that's why an automobile engineering system is there. Suppose a car, when you consider a car, definitely that particular car, the design of that particular car, the internal structure of that particular car, the internal ignition structure of that particular car entirely depends on all these particular areas. So if you open the board, you can see that. So now some examples I will tell. Just now I told about the embedded system. We need to have control to achieve some particular application. The first one is the domestic refrigerator. Everybody knows that in every family nowadays, the minimum thing that every family, a moderate family, will have a refrigerator. So here, the why do I want to use the refrigerator to maintain certain temperature, and we will use this refrigerator. So we will, in order to decrease the temperature, control the temperature, we need to use some particular the control. So the process of control can be done by a conventional electronic circuit, or it can be done by a small embedded computer. So if you use the embedded computer, would be designed simply to replicate the what we can say minimalist control process described above. So if you see here, there is embedded computer chip. So this is embedded in this particular compressor to maintain that particular temperature. This is one example. Then the second one is car door. So if you see the internal diagram of the car door, We have the central control, then airbag, steering, dashboard, then climate control, driver's seat, radio and seat, CD, left door, the right door. So all these particular things that we are observing in a particular car door. So here the central locking can be introduced or alarm sounded if the door is not locked. So this we are observing. Suppose even now there are advanced systems that has come. Even if you touch the if you touch the car, thefting that occurs, there is an alarm that comes. So this is one type of what we can say the control we have over that particular automobile system. Then another example of embedded system is a doctor is configuring a cardiac pacemaker, so inside his patient's chest while sitting 2 kilometers away. Okay, this is another example. Then ping pong game, as we are seeing, our children are playing with the help of the mobile. So overall, if you see, more than 30% of the cost of a car is now in electronics, and 90% of innovations will be based on electronic systems. So as you see, the car, so all these particular the units which belong to what we can say that some type of control we can have in the particular car. Now, so these are the different controls, functions of controls that we have. There is a trip calculator. So earlier days, so when you want to travel from one place to other particular place, if you want to know the distance traveled, the overall time that took place, so we need to what we can say empty the tank, and we can fill out the diesel or petrol, and then once if you start, you'll note down the reading, and then after completing our trip, then we will see the how many kilometers it traveled, and then based on that we'll calculate the time as well as the fuel consumption that we can calculate. But now the trip calculator, if you reset and if you start, then automatically once if you go and come, so then automatically it will indicate how much time it took place, how much fuel it consumed, we will know. So those are the, this is one simple example that I am telling. There are different types of control units are there. We can have the control. So in all these things, we are achieving the control by embedding a particular the unit to have such type of a specific application. So these are, if you see central processing units in a car seat, if you open the seat down, so we can observe different things. These are some examples for idea's sake. I am showing that front back motion, seat tilt motion, control button interface. And these are the CPUs in car. See how many Pentiums that are involved in the car. This is one guided vehicle example. So if you want to design a simple automated guided vehicle, or now people are talking about a simple robo, automatic robo. So this is actually, we have a unlock to digital converter, then PIC controller, and then different types of sensors, left side, right side sensors that we can use it. And then there is a motor to have a control, and then we have a ultrasound ranging module. Okay, so this is one type of a guided vehicle. If you want to design this particular guided vehicle, so these are the components that are needed. If you see here, there is, it is linked with the digital electronics. There is a microprocessor is there. Then there is a sensors and actuators are there. Then we have a motor is there. So that means it is linked with all interdisciplinary areas that are needed. Now, what are the processing units of an embedded system? There are different types of processing units in embedded systems we have. One is we can, a processor is an important unit in embedded system hardware, microcontroller, some type of the what we can say embedded system consisting of microcontroller, and some type of embedded system which consisting of DSP processor, and commonly microprocessor, microcontroller, or a DSP, which we can have based on these particular processes, we have different classifications. You can see that. And another unit is there is application specific system processor. SIP also is there. And then somewhat sophisticated is multiple processors in a system that we can have. So like this, we have four processors are there. One is microcontroller. The second one is an embedded processor, that is an DSP processor. The third one is an application specific system processor, and fourth one is multiple processors in a particular system. Is it okay? Is it audible clearly? Hello? Is it audible? Is it audible?
Yes, sir.
Okay. So now we are seeing the definition of the embedded system. Then what are the areas that are linked with? Then processing unit. Now, based on this particular processing unit, we have categories of embedded system. Number one is standalone embedded system. A standalone embedded system works alone itself. It is a self-contained device. So here, what we will do is it takes either digital or analog inputs from input ports, calibrates, converts, and processes the data. So, for example, the entertainment device like a video game console, MP3, digital camera, or microwave are such typical systems fall into this category. Then another one is the real-time embedded systems. Here, real-time embedded system, a system is said to be real-time if the response time is critical. In other words, some particular work must be done in a specified time period. So here in the real-time embedded systems, we can see that two functions. One is the correctness, another one is the time constraint. These two are very, very important. There are two types of embedded systems we have. One is hard real-time, another one is the soft real-time. The hard real-time is for a hard real-time. So the immediate real-time system, the completion of an operation after its deadline may lead to critical failure and result in a live loss or property damage. So that's why here in the hard real-time, the time is very important and the correctness is very, very important. So suppose when I say an example airbag, car airbag is there. So after some time accident took place, after half an hour if airbag opens, then there is no use. So dead body come and occupy that particular airbag. So that's why there in the airbag usage, the time, the correctness function is very important. That category is called hard real time. Whereas in soft real time, so the response deadline, but lateness can be tolerated in some degrees. Suppose when you take the microwave oven or washing machine, so we don't bother much about this. Even if some time took place also, there is no problem to worry much about the function. So first one is standalone system, second one is real-time embedded system, third one is networked embedded system. Networked embedded systems are connected to a network with network interfaces to be accessed or access other resources. So local area network, wide area network, or internet. So the connection can be wide or wireless. So different types of the networks which we can connect, and we can have the embedded system, that is called the network embedded system. So another type of the classification is, as we have seen that based on the processor, multiprocessor, microprocessor, microcontroller, or DSP processor, we have another classification. One is small scale embedded system where the 8-bit or a 16-bit microcontroller will use. In the medium scale embedded system, there is 16-bit or 32-bit microcontroller or DSP will use. And in the case of sophisticated embedded system, we'll use multiple processes like scalable processor or configurable process or programmable logic arrays, which we can use. Coming to the embedded system configuration. So if you see the typical computer system configuration and typical embedded system configuration, the difference that we are observing here In the case of typical computer system, we have a hardware and operating system is the different, what we can say, there is a hardware separate, operating system is separate, and the programming part is separate. But in the case of the embedded system, we have a hardware and user program which includes the operating system components. That is the difference that you can observe. This is a typical embedded system, where in the case of typical embedded system, we have the algorithms for digital control, data lagging, data retrieval and display, operator interface, and we have a typical embedded system which consisting of these particular components. So we have a remote monitoring system, interface engineering system, we have a real-time computer, so operators console, database, real-time clock. So these are actually the a typical embedded system where we can have all these components that we can consist. So coming to the components, so quickly I will discuss about the components. One is it embeds the hardware similar to computer as we have seen. Then it embeds main application software. Along with the hardware, we need to have the application software. Then afterwards, it embeds a real-time operating system that supervises the application software running on hardware and organize the access to a resource. Okay, so these are the three, what we can say, the major components in any embedded system which we can have. So hardware, application software, and in order to supervise the application software whether running or not using a real-time operating system. So this is the structure of the embedded system hardware, where we can have all these things: processor, timer, interrupt controller, program memory and data memory, serial communication port, parallel port, input device interfacing, like that, the power, all those things. I'll try to show that. Then this is the typical embedded system organization. So any particular system, if you want to design, so we have a central processing unit, corresponding software will be there, then memory, then we have the field programmable gate array. Then from the sensor, we'll take the input, then that is in the analog form, that should be converted into digital, analog to digital conversion. Okay, so then the digital is converted into analog conversion, and remaining things are actuators. So electromagnetic backup, the external environment. So all these particular the accessories which are connected to this particular CPU. This is actually a typical embedded system organization. So the overall, after seeing all these things, we have a different the components: general purpose processor, application specific system processor, microprocessor, general purpose processor. So these are already we are familiar with these particular things. I am not touching this microprocessor or a microcontroller. Okay, so microprocessor is one component, microcontroller. Okay, so there are different types of microcontrollers people use. Okay, then as we have seen that this is the classification of different microcontrollers that people use: 8051 family, pick controller, the Hitachi, okay, 68HC11X. So this is this type of the microcontrollers they will use in the case of small scale embedded system. Okay, so then medium scale embedded system, 16-bit microcontroller. Then a large scale embedded system, people use the 32-bit microcontroller. And still Hitachi, the family they will use for a higher end the embedded system. Various functional circuits. I'm not touching the microcontroller part. Then power source, low voltage operation, clock oscillator circuit, system timer and real-time clock, reset circuit, power up reset and watchdog timer set, memory, So these are different types of components. Already I told. Even in memories also, we have a different types of memories: internal RAM system, internal cache, external RAM chip, flash memory, ROM, memory address. So all these type of memories, the various forms of memories in the system. Then input, output, and IO ports. These are the cases. So these are the just for idea. I'm showing all these particular components of an embedded system hardware: pulse dialer, modem, transceiver, interrupts handler, GPIP link, then embedded system development. So basically, if you want to develop an embedded system, so we need to have this particular workstation, development workstation, then an embedded system, simulated signal source, workstation interface cards, and test hardness. So coming to the metrics of embedded system, so when you want to design an embedded system, there are certain metrics are there, there are certain characteristics are there. So all those metrics and characteristics just we'll try to discuss. So if you want to design an embedded system, the first design metric is power dissipation, performance, process deadline, user interface, size, engineering cost. So what should be the initial cost of developing? Manufacturing cost, cost of manufacturing each unit, flexibility in the design, prototype, time taken in days or months, development time, time to market, system and user safety, maintenance. So these are actually the what we can say that the metrics for an embedded system. Any person who want to design an embedded system, he should have all these things: the power dissipation, performance, process deadlines, user interface, size, engineering cost, manufacturing cost, flexibility, prototype, development time, time to market, system and user safety. Coming to the characteristics of embedded system. So embedded systems are designed to do some specific task rather than be a general purpose. That is our main goal actually. So an embedded system must be used for a specific purpose. And the embedded systems are not always separate devices. Most often, they are physically built in the devices they control, embedded into the system. Then third one is the software written for embedded systems is often called firmware and is stored in the read-only memory. Must be dependable, maintainability, availability, safety, security. So these are the different types of what we can say the characteristics of an embedded system which we need to have these characteristics. So we have seen the design metrics, then we have seen the characteristics of embedded system. So must be so when you want to design an embedded system, it should be energy efficient, the code size efficient, runtime efficient, weight efficient. Then it should be cost efficient, dedicated towards a certain application. So dedicated user interface. So normally without using a mouse, keyboard and screen. So sometimes as we have seen that in the case of the network embedded system, the suppose if you don't have the network connection, in terms of the wireless connection also, we need to make our system should be dedicated interface. And many embedded systems must meet real-time constraints and frequently connected to physical environment through sensors and actuators. Dermot. So these are the characteristics of an embedded systems which we must have. There are certain constraints. So most of the time, there are some typical embedded system constraints which we have. In the case of typical embedded system constraints, One is small size, low weight. Small size means handheld electronics, and low weight transportation application, weight cost money. Low power is battery power for 8 hours, harsh environment. So even in the fluctuations, power fluctuations, we need to use the embedded system. Safety critical operation, extreme cost sensitivity. How do I can embed a software in a particular system? So for a specific application, I need to embed, execute the software that is specific to give a given application. This is like actually we know that a stack pointer. So how we can push and pop operation like that here also every specific what you can say location will have an address. The software which we are embedding here is called the ROM image or some firmware we can say. Just as an image is a unique sequence and arrangement of pixels, embedded software is also unique placement and arrangement of bytes for instruction and data. And the software in processor specific assembly language. So basically, it is a mission specific assembly language program. Using the assembler, the mission code we can convert, and then mission codes ready for locating at various addresses the software. Then from the library needed mission codes, then bytes for linked program from their device programmer and embedded system ROM memory will come. So like that software in a processor specific assembly language. So there are certain program models for software designing. So this is another what you can say major research domain in the case of the embedded system. The different models that are employed during the design process of embedded software are: one is sequential program model, another one is object oriented program model, then control and data flow graph model, finite state machine model, then multi-thread. Like that we have different types of models in which we can what we can say develop the code. So first one is the sequential program model. As we know that we can suppose any particular general problem specification is there, we will try to develop the state diagram, state table, and then we can develop the if it is a design oriented structure, or from the description we can develop the code by using the hardware description language, and then we will develop that model. Or in the case of object oriented model, so based on the module based, I can explain the hardware. Then there is a control and data flow graph. By using the synchronous data flow graph or multi-thread graph, I can draw that. Then there is another important one is finite state mission model. So in the case of finite state mission model, so there are two types. One is the deterministic model, another one is non-deterministic model. So based on the present state, the next state, and the current input, we can design a particular deterministic circuit. That is called the finite state mission for data bath. So like this, we have different models to develop the software. So there are different types of software tools for designing an embedded system are there. The editor, interpreter, compiler, assembler. Then we have a cross assembler, simulator, source code, different types of software tools people use for designing an embedded system. So there are a number of the what I can say software tools are there. So these are the common type of embedded system functions. And coming to the operating systems for embedded system devices, this is also an important concept. So there is exclusively a topic called real-time operating system. Most of the people used to study about real-time operating system. So operating systems actually are classified into real-time operating systems and non-real-time operating systems. In the real-time operating systems, the operating systems which guarantee responses to each event within a definite amount of time. This type of operating systems is mainly used by the time critical applications, as we have seen that hard real time, soft real time. So examples commonly used are VxWorks, OS9, or Linux. And non-real time operating systems do not guarantee defined response time. Those systems are mostly used if multiple applications needed. We will use Windows CE and Palm OS are example. So basically, the embedded system design involves hardware and software co-design. Okay, so co-design of software and hardware. Earlier days, people used to design in a system in a traditional way. That means separately they will do. But in the case of co-design, that is called the concurrent design. What is co-design means? It is synergism of assembling of all the particular units. That is the hardware as well as software. Parallelly, they will design a particular system. So that is actually hardware software co-design. So coming to the design requirements of an embedded system. So timing aspect is very important when you want to design an embedded system. Then power consumption, cost sensitivity, size and weight, safety and reliability, time to market, and others. So timing is very important. Then power consumption, cost sensitivity. So all these particular parameters which we can observe here, different types of application advantage, you can see that. So these are the digital design platforms for embedded systems that we can use it. So these are the design challenges as we have seen already. Okay. So these are actually the six stringent resource constraints. One is compact systems, simple processors, limited memory, quick response, good throughput, and low power. So these are the design challenges which you need to consider when you are designing a embedded system. So this is actually the design process. So up to now, we have seen various aspects about the design metrics, characteristics, challenges, and what are the constraints in the embedded system design. Now coming to the, if you want to design an embedded system, what are the steps involved while designing a embedded system? This is very, very important concept. Number one is abstraction. So when you want to design an embedded system, first step is abstraction. So each problem platform component is first abstracted. So let us consider to design a robo system. The problem of abstraction can be in terms of control of arms and motors. So based on that particular problem, so how many arms, motors, the requirements, that is actually the design specifications that we can get it from the statement of the problem. So most of the time when you want to do any particular design or a research problem, if you want to take up, first of all you should have the comprehend analysis of your abstract. If you know the comprehend analysis of your abstract, then only you will know your system configuration. So basically, suppose if you want to design a particular laptop, or when you want to purchase a particular laptop, so immediately the people they will ask, what are your requirements? So for what purpose you want to use the laptop? Suppose a simple i3 processor, I can use it. And there is i8, i7 is there, i8 is there. So core processor is changing. So same laptop will do the work. But and sometimes There is a gaming a laptop will be there. There we don't use the Microsoft. Whatever system that I'm using, I'm not using the Microsoft. So there is actually the different what you can say operating system I can have. So without having the abstract way of clear analysis of your problem, it's difficult to have the design specifications of your thing. So if you want to design a robotic system, the problem of abstraction can be in terms of control of arms and motors. The second one is the hardware and software architecture. Architecture should be well understood before design. So once if you have a abstract way of the analysis, then hardware and software architectures you should design. So you should have idea about hardware and the software architecture. Then after knowing the abstract way and hardware and software architecture, the extra functional properties required in the system being developed should be well understood from the design. Then fourth one is the system related family of design. Families of related systems developed earlier should be taken into consideration during the design. So earlier, if anybody has done that particular problem, the system related details that we should know. So first one is the abstraction, hardware and software architecture, extra functional properties, system related family of design, then modular design. Modular design concept should be used means, so this is hierarchy way of composing our problem into different modules. After composing our problem into different modules, so then we can module wise we can take up. So function independence, cohesion, coupling. So this each particular modular design should ensure that they should be effective in the function independence, cohesive, then coupling. So modules must be clear understood and should maintain continuity. Also appropriate protection strategies necessary for each module. Then sixth one is the mapping. Mapping into various representation is done from software requirements. For example, data flow in the same path during program flow can be mapped together as a single entity. So after modular design, mapping is very important. Then afterwards, user interface design. So once if you have this particular mapping, then user interface design is an important part of design. Then refinement, each component and module design needs to be redefined iteratively till it becomes the most appropriate. So if you want to design embedded system, these are the design steps or design processes. 8 steps that are needed to design an embedded system. I'll repeat. First one is the abstraction way of designing. Second one is hardware software architecture. Third one is extra functional property. Fourth one is system related family of design. Fifth one is modular design. Sixth one is the mapping. Seventh one is the user interface design. And the eighth one is the refinement. So like this, from the design process, all these particular activities for software design during embedded design which we can come across. So some of the examples of embedded system, there are a number of examples are there we can have. So these are different types of examples nowadays. More than these things, we can have multiple applications that we can have in the case of mobile computing, wireless networking, banking, telephony security, defense, aerospace communication, automotive, DVDs, motor control system, networking system. Okay, like that, different types of examples of embedded systems that we can achieve. So you see here only more than 25, 37. So this is system design process. So I'll give two examples of embedded system. Number one is the automatic chocolate vending machine. In the case of automatic chocolate vending machine, This is actually the diagrammatic representation of the automatic chocolate vending machine. We have a LCD display or touch screen for the user. So this is the idea is automatic chocolate vending machine. If you drop a coin, then we can, depending upon the cost of the chocolate, we can have the sorry the chocolate we can come. Okay, there is a microcontroller based hardware, then real time operating system, then we have a embedded software, USB wireless modem, then chocolate and refund coins collection bowl. There is a mechanical coin sorter and a keypad for user interface. Okay, so these are actually the diagrammatic representation of the automatic chocolate vending machine that we can observe. See here, there are the hardware components as well as software components what we need to have. Okay, so there is a keypad on the top of the machine which enables the child to interact with it. When buying a chocolate, the owner can also command and interact with the machine. It has an LCD display top of the machine. It has a coin insertion slot. Then it has a delivery slot so that child can collect chocolate and coins. It has an internet connection port using ESP based wireless modem so that owner can know status of ACVM sales from the remote location. So these are actually the components that we need to know. The functions, the displays the GUI. If child wishes, enter the contact information, suppose birthday, name. Okay, it will give the welcome mission. And first coin inserted, a timer also starts. After 2 minutes, will display a query to the child. If the child does not insert sufficient coin, again it will ask. Within 2 minutes, if the sufficient coins are collected, it displays message, thanks, wait for the moment, please deliver the chocolate. So this is actually the description of the chocolate vending machine. So we are familiar with this, and in the airports and railway stations, we are observing this how this particular the chocolate vending machine works. In fact, if we are not able to know the chocolate vending machine, we can see in the railway stations weighing machine will be there. If you insert a 1 rupee coin or a 2 rupees coin, then automatically depending upon our weight, it will give a card. Some particular words will be there, and the weight also will be written on that particular card. So that is the actually the abstract way of the description about a particular system. Now based on that, I should have the hardware units of automatic chocolate vending machine. What are the components that are needed? One is microcontroller, RAM, ROM, flash memory, the timer and interrupt controller, then internet broad connection. Okay, then specific what you can say coins, different denominations, power supply. So these are the hardware components. So this is actually the description of the abstract way of description of the problem. Okay, so these are the functions that we need to do it. Then these are the hardware units that are required. Then coming to the software components, embeds the following software components. One is the keyboard input read task, display task, read coins task for finding coins, deliver chocolate task, TCP stock processing task, and TCP IP stack communication task. So these are the software components that are needed in the automatic chocolate vending machine. Okay, so this is the automatic chocolate vending machine is an example. Okay, is it understood? So this is the abstract way, functions, hardware units, and then software components. Like this, we have a mobile phone design process. In the case of mobile phone design process, hardware unit. So in the hardware unit, DSP, flash memory, peripheral circuit, direct memory access controller, LCD controller, battery. Then similarly, software components, operating system, Java 2, memory, file system. Like this, we have the software components. Okay, and in addition, the mobile has Windows. We have operating system, touch screen, memory stick, Outlook Internet Explorer application. So these are the two examples: automatic chocolate vending machine. Another one is the mobile phone that I have given example. Now coming to the system design process exam, typical embedded system. This is a flight control system. We have a autopilot controller, inner loop controller, airframe. Then we have these things, customer view. This is the engineering view of that particular system. So how to design the embedded system using FPGA? Once if you have an idea about embedded system, how you will do design using FPGA. So the idea to go for the FPGA is, one is reconfigurability. That is, field programmable devices can be configured at any time. So reconfigurability means they are compatible. The designers can integrate modifications or do complete personality changes. And software design is, the hardware is defined by software like languages HTL. So these are the two cases that we observe in the case of FPGA. Reconfigurability, another one is the hardware description language. We can develop, the designers can develop, simulate and test a circuitry fully before running it on a field programmable device. So like this, we can use this depending upon the task. I can design embedded system using FPGA. So high speed, reliability, IP protection, and reuse. So these are the major the benefits why we will go for the FPGA. So basically, the common design tools for FPGA vendors is, we can use Xilinx, Altera. Okay, so these are the cases that we can use in the case of the FPGA vendors. So as we have seen that the robo controller with robo signals, how we can interface. There is a Xilinx, and we can interface this particular robo through a particular system. We can interface, and then we can design a particular system. This is interfacing a FPGA based robo controller with robo signals. This is the, what we can say, the example of the how the embedded system application interfaced with the interfacing a FPGA based robo controller with robo signals. So these are different opportunities. In the case of what you can say, the embedded control, we have a hardware design engineer, software design, device driver, kernel developer, network engineer, RTO programmer, software engineer, all these things which we can achieve in the case of the embedded system. So these are the companies which are working on embedded systems and applications. Okay, so IBM, Lucent Technologies, Mascon. Okay, so different types of the companies, they are working under this particular thing. So that's all about the idea. Hello, hello, is it audible?
Yes, sir. You're audible.
So any clarifications or questions? This is the complete idea about the embedded systems, the design challenges, metrics, and the examples I gave. And in fact, the hardware software co-design I have not touched in that particular part. So this is about the complete overview of embedded systems, and two examples that we consider: the automatic chocolate vending machine and mobile, and then how we need to design this particular embedded system, and then some of the aspects about embedded system. Okay, so any questions regarding the?
Till now in chat box, there is no question I can see in the chat box right now.
Yeah.
So, dear audience, you can post your questions.
Hello, madam. You may also ask the participants to unmute and ask if they want to.
Okay, okay, madam. Dear participants, you can unmute and also ask questions to sir.
Yeah, it's welcome. Please.
You can also post in the chat box the questions.
Because there are questions you can ask. Otherwise, 11:20, I have a meeting. Our honorable governor will address our entire institute. So that's why I want to attend that particular program. Our
Okay, sir.
governor is addressing our faculty at 11:20. Okay,
Okay, sir.
so another 5-10 minutes I'll wait. So you can ask.
Hello.
Hello.
Good morning, sir. I am Saurabh Bhattacharya.
Yeah.
Yeah, sir, I want to know one thing, sir. If someone want to design one embedded system using
Yeah.
some hardware and software, then what are the platforms basically we need?
Yeah, that's what I have given the example about one automatic chocolate vending machine. So
Yes, sir.
normally, suppose if you want to design a simple robo system,
Hmm.
okay, is it audible?
Yes, sir. Yes, sir.
Is it
Yes, sir. You
audible?
are audible, sir. Yes, sir.
Yeah, normally a robo, if you want to develop that, I have shown that. So suppose if you want to do a prototype model. Okay, so to
Hmm.
do the prototype model, what we need to do is, so you depending upon your problem, like any movement or picking of an object, and then to pick up a particular object, you need to write some particular code, and then you need to get some analog to digital A to D converter, D to A converter, then a simple microprocessor. So these are the hardware components that you need to do, you need to have. Then we need to have, either you can go for a Xilinx model or the Altera model. So you can there are Spartan kit is available, or we can have a Xilinx kit is available. So you can
Hmm.
take that, and then you can write a program in a VHDL, hardware
Hmm.
description language, and
Hmm.
then you can write that code, and then you can dump that, and you can interface that with the help of this particular FPGA and this particular designed thing. You need to interface this particular robo with the FPGA. Suppose these days actually there is a Python oriented kits are available. Actually, Arduino boards are coming. With the help
Hmm.
of Arduino boards also, we are doing that particular thing. So there
Yeah.
actually in place of microcontroller, you can use the PIC controller. Depending upon your processor, you can have such type of thing, and then you can interface that. That is
Hmm.
actually a simple example.
Sir, actually, I want to ask the question in a different way. Suppose, sir, I want to design one multi-transducer interface system using some hardware. And if I use the FPGA board, So, sir, it takes a large amount of cost. So, sir, there are any other way to minimize the cost?
Yeah. You are telling the multi-transducer.
Yes, sir.
Is it right?
Yeah.
Yeah, transducer basically it will convert one form to other particular form. Let us consider what we can say piezoelectric transducer you want to develop. Is it right?
Yes, sir.
Hello.
Yeah, right.
So piezoelectric transducer is that the displacement is converted in that pressure is converted into a voltage. So then the same thing that suppose I'll give one simple example because now we applied one project also. Suppose on the road actually vehicles are moving. Is it right? So to know that particular the low power generation we are developing actually. So the vehicle it is moving based on that particular vibration. So that is actually we are generating the solar energy based on that particular vibration principle. There is a piezoelectric device we can keep, and then that is converted into an electrical signal, and then in turn that energy is converted into a particular battery type. So instead of using the particular FPGA kit, so with the help of different hardware units I can design, and the remotely I can have this as I told you that there is a we can have the what we can say the internet connection, and we can develop the code, and in turn remotely we can access that particular code through the what you can say cloud.
Hmm.
So that is actually in terms of transducer I am telling instead of cost effective.
Okay, sir. And sir, what is the nominal cost of implementing hardware using Spartan board or FPGA board?
Spartan board normally it will cost about even 40,000 to depending upon that, because minimum cost of Spartan kit is 45,000. You will get a good Spartan 3x. We will get it. Spartan
Um,
3x. There is a
yeah.
6x, 7x is there. But
Means are
roughly
using
75,000 we can have the entire kit. I think in so many institutions they are buying that particular kits, and they are coming and they are providing that kits also. It's not now. I think even for 15,000 we can get this Spartan kit.
okay, sir. Okay. Means if we want to design a project, it will take a cost of approx 60,000. Right now, sir?
Yeah, that is especially if you want to do in the FPGA.
Yeah.
Okay. Suppose if you want to do the same work with the Arduino board or the Arduino board, so then roughly it will cost within 3,000. You can do that.
Yeah. But the real-time operating concept will not be available in case of Arduino board.
Yeah, correct.
Yeah.
Yeah.
Okay.
Yeah, you are correct. You
Yes,
are
sir.
correct.
Oh, thank you, sir.
Good, ma.
Sir, till now, no questions are also posted in chat box. I would like to request the audience to ask questions if you have. Sir is already waiting for you.
If there is no question, I think it is better to close the session because Sir has another schedule.
Yes,
Yep.
sir. Yes.
Because I have our governor, the
Yes, sir.
Telangana government addressing all faculty. That's why.
Yes.
You please present the certificate to sir.
Yes.
Yes. Yes.
On behalf of the department, I am presenting the certificate as token of appreciation to Sir. Sir, just a minute, Sir.
Sir,
Yeah.
I have ready. Can I share, sir, or can do, sir?
Yes. No. I have also the certificate.
Oh, okay. No problem.
Is it visible, Sir?
Yeah. Thank you so much. Ma. Okay. So all the best participants. I think Dr. Namita Madam have my email ID. If you have any questions further, you please contact me through Namita Madam or the coordinator. Okay.
Yes, sir. Okay, sir. Yes.
Okay, ma'am.
Thank you, sir.
Thank you, madam. Thank you. Shall I close, madam? Shall I
Yes,
leave?
sir.
Thank you.
Yes.
Thank you, Vedant.
I think our next session will be starting from 11:30.
Yes, schedule time is 11:30.
Let me check if I will call sir. If let me see if he joins early. If he can join early, okay? Let me check.
No, madam, I am checking. He is not joined.
Yes.
Actually the time is 11:30. That is
Yes,
why
yes,
he has
yes,
not joined.
yes,
Okay.
yes.
Now let me see if I can call him.
Had better to.
এখানেই বসে রয়েছে। ফোন করলে কথা হবে তাহলে। না না, তাহলে কও শুনতে পেতো। না 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 না, তোমার ওটা ভয় ঢুকে যাচ্ছিল। না না না, বলে না।
Kamalika madam, please mute.
Yes, yes.
Welcome, sir.
Welcome. Good morning. Actually, I clicked another link that was to common mail, so I was not
Yeah,
getting
yes,
the
sir.
response.
Okay, sir. So once again, welcome to all the participants and welcome, sir. Before I go ahead or before the session restarts, let me read out the short profile of Professor Mukhopadhyay. Professor Ashish Kumar Mukhopadhyay is AICTE nominated Margdarshak for mentoring different engineering institutions. He was associated with some institute as visiting distinguished professor as well as advisor. Presently, he is the vice chairman of IETE Kolkata Center, as well as the vice chairman of IEEE Circuits and Systems Kolkata section and advisor of Eureka Scientific Research Foundation. His past assignments include Group Director SRGI Jhansi, Director of BITM Shantiniketan, Principal of BCTW Durgapur, Dean Academic as well as HOD EC and of CSC Department of BCREC Durgapur, Professor and Head of CSC and NIT Agarpara, Kolkata, that is Narula Institute of Technology, as well as he has been associated with the Kolkata Engineering College as Assistant Professor EC and Chairman of Central Library at NERIST, Northeastern Regional Institute of Science and Technology, Itanagar. Earlier, he took voluntary retirement from the EC department, IIT Kharagpur. He was a member of Board of Studies, the West Bengal University of Technology, Kolkata, as well as Vidyasagar University, Midnapur. His past assignments included being a member of MC, CSI Kolkata chapter, honorary secretary, the Institution of Engineers, Kharagpur Center, co-chairman of technical committee, 14th Indian Engineering Congress, IIT Kharagpur, as well as ex-committee member of IETE Bardhaman, as well as and chairman of CSI Durgapur chapter and governing body member in 4 engineering institutions and 1 government school. He has published more than 100 research publications to his credit in international domain and co-authored 3 international book chapters published by IGI Global USA. And he is also the editor of 2 international book proceedings. So, with this, now I would request Sir to start his lecture. So, now the session has been handed over to you.
Thank you,
Welcome, sir.
Naumita, for your introduction. Before I start sharing my PPTs, I would request the listeners, audience, that if they have any questions, they may note down the slide number during the presentation, so that at the end of the presentation, they can refer to the particular slide number and ask a question. It would help me in answering the question. With this, I first of all thank the organizer, particularly HOD Electrical Department, for inviting me to be associated with this program. And I also thank all of you who have joined this and listened to this lecture program. Let me share. What's the problem with sharing? There are some hazards with online presentation, like getting connection, all these things. So please bear with if there is any difficulty during the presentation. What is that? It's not being shared, no? Cannot share. What happened?
Yes, sir. Your screen,
It is coming, sir.
has been. Yes,
But
yes.
I cannot see. Anyway.
But your name is displaying, sir.
Oh, anyway, let me then.
You just open the PPT, sir. Yes, sir, it is visible.
Am I audible clearly or? That's
Yes,
very
sir.
important.
Yes,
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 sir,
yes.
audible.
Audible, visible, both should be there. Okay. So my topic is smart grid with enabled technologies for distributed power generation system to match the topic of this virtual STTP. Recent trends in IoT and embedded system-based monitoring and control of distributed generations. I'll introduce smart grid, which is for monitoring and control of electricity transmission and distribution system through grid using smart technologies which interconnects different system elements through internet and enhances the resilience of the network. Resilience means there is the hazards of the natural hazards of networking, which is coming to the environment or otherwise. It will also help the electrical consumers to feel as an owner of the energy transmission benefit as and when new technologies are introduced to it. Smartification of the energy system introduces a range of societal conditions and consequences due to heavy impact on our daily life. Now start with depicting the traditional electricity transmission and distribution network. We know that we are dependent mostly about 65% of the power generation is through thermal and some are hydel, etc. So these captive power plants are transmitting the generated power, which is kept very high voltage so that the current passing through the conductor is minimum to reduce the transmission loss, I square R loss. So if he is very high, I will be less. So initially it is kept at 400 to 800 kilovolts through extra high voltage towers. It is transmitted and reaches a territory area where to end up with the step down transformer. It is made to 220 kV or 132 kV as per requirement. Again, this is transmitted. It has multiple directions. Each direction will have that 220 kV or 132 kV lines, and it will reach the substation to 33 kV. Then this to 33 kV feeder network, and ultimately further step down will reduce to 11 kV or three-phase 415 volt supply for the consumers, which will be distributed in either to the industrial consumers or domestic consumers. Industrial consumers will require three-phase distribution, whereas in the domestic consumers will require single-phase distribution. And in each distribution, there are circuit breakers, load breaking switches, remote terminal units, etc., etc. These elements are very essential for the from generation to reach the consumer end. Now, what is grid? It is a parallel and distributed system of geographically scattered autonomous resources. That means resources which are independent, they can control themselves for coordinated activities such as sharing of power, selection, and problem solving based on resource availability, capability, cost, and consumer requirement for desired quality of service, and which is dynamic in nature. Every time load is changing, every time the resource available is changing, and other issues are changing. Now, if we consider electric grids, that autonomous resources, which I talked about in case of grid, this is nothing but a network of transmission lines, substations, transformer, and other that deliver electricity from remote power plants to customer premises. Now, electric grid power simplifies the job of electricity users just like a computer grid does for the computer users. So the computing power is available easily with simple methods. So primary objective of this electric grid is to transport or distribute and bring safe and effective energy right from the generating stations to the from the predictable sources to the millions of consumers who are located geostrategically throughout the territory. Now, technological evolution of electric grid has not taken much during the last century. The architecture remained almost same, but the emphasis on efficiency, reliability, sustainability in energy generation and demand, substantial change is required in this existing distribution system. So the change is required with the help of enabler technologies like information communication technology as a key enabler. And there has been a paradigm shift in electrical grid technology for research efficiency, for energy efficiency, reliability, to integrate renewable energy resources using those enabler technologies, using ICT tools and other technologies like cloud computing, embedded system, and Internet of Things. Now, talking about the architecture of grid, it has 5 layers. The fabric layer considers the physical hardware resources like storage, sensors, computing servers, network, etc. Connectivity layer connects resources request to the actual resources. That means it establishes connections, communication connections between the utility and the user with the required permission, data security, etc. Then resource service layer, which runs an application of various hardware and software resources under collective operations. Collective layer monitors and make diagnostics and replication and authorization and authentication this part for the users, consumers. And finally, the application layer where software development kits reside with all application control programs, including embedded system also. Now, grid has 3 topologies. It could interact intra-grid, that means within the grid and organizations where the trust is based on individual contracts. Now, when the grid communicates and connects with the external resources of a consortium of organization, it becomes extra-grid. It uses virtual private network or VPN, and trust is based on business-to-business contract, B2B contracts. Now, all grids may communicate among themselves with the 3rd topology, intergrid, for global sharing of resources through internet, where trust is based on certification by the in that particular grid, which is involved in this sharing. The grid service and type, while utility computing service, which requires utility grid for a market-based grid computing, leasing, and delivering grid services as ICT utilities. Knowledge services using the knowledge grid, the way knowledge is acquired, processed, and managed, like data mining. Interaction services using interaction grid for e-learning, virtual tables, group communication, access grid, gaming. Application service with the help of ASP grid which is web-based, to access the remote software, libraries, and license management like NetSolve, etc. Data services using data grid for collaborative data sharing generated by instruments like sensors and persons like various grids, Sun, Napster, etc. Finally, computational services use computational grid for pulling computing power from different grid sources. Now, all these are in a sequence, right from utility to computation layer, with most emphasis on users for the utility grid, and computational grid is most emphasis on infrastructure. So this moves in that way. Now, these grids, normal grids, they face a lot of challenges. First is the security concern. Very important for is when there is a grid, there must be some computer. And when there is a computer, there is a concern from security. Plus, uniform access. Because the users and consumers are heterogeneous. The resources are also heterogeneous, different type of power sources. So accessing those in a uniform way is a challenge. Then data is decentralized. It's not controlled by a single person. All our autonomous agents are doing that. So managing that is a challenge. Now, system management, huge system is required for each resources. So that management of the system and their network is also a concern or challenge. Now, electricity company, organization, they sell electricity to the consumers, and they cannot charge huge amount just for their computation infrastructure. Therefore, you have to think of the economy in computational activities so that the consumers are not affected much. Then building grid applications. Grid applications are various. For example, we can build one application to which we using sensor to monitor the some natural calamity like Amphan, something like that. But or we can have a sensor just to sense the weather, very simply, just sense weather. But when it senses the weather, it must also support the adverse weather condition like Amphan, etc. So when we build application, it has to be justified. That means it should be supportive to all situations. That is also a challenge. The resource allocation and scheduling are the two very important for any grid. And when we do for in a smart way or in advanced way, naturally a lot of energy is devoted, a lot of computational power is required for this allocation and scheduling. Now, how to meet these challenges? We need some enabling technologies. What are those? First is that distributed computing, utility computing and grid computing. Then we need system management for automatic computing, data center automation. We need embedded system, the hardware part for virtualization, multi-core chips have to be developed, and internet technologies, the service-oriented architecture, web version 2, web services, etc. The question is that these enabler technologies all require many services and many resources. Now, this power plant generation system, they may not afford to have that huge infrastructure. So we need some sort of facilities like cloud computing. Cloud computing will take care of this huge data management and resources required. So these enabler technologies will enable to take up the challenges mentioned in the previous slide. Now comes smart. It can be defined as an electric grid that uses ICT tools to collect, process, and analyze data on information about the behavior of both the electrical power suppliers as well as the consumers in an automated fashion. Look, that it is concerned about not only power supply but also consumers. These are very important. The information technology ICT, the information technology part requires embedded system and power electronics, monitoring and control systems, decision support system, data analytics. We need machine languages. For communication, we need a telecommunication network, which will be the backbone of energy network. We need internet services, and we also need intelligent consumer management system to make this smart grid possible. The smart grid network is nothing but combination of the computers, the intelligence, that intelligence means it could be artificial intelligence, it could be computational intelligence, then networking abilities, communication abilities, and with the existing dumb electricity distribution system. We add those all things, the system will become smart. Now, the digital technology that allows for two-way communication between the utility and its consumer and the sensing along the transmission line is what makes the grid smart. That means in normal traditional system, the consumers cannot talk to the power station, cannot give any feedback. But in case of smart grid, they have a digital platform which allows the two-way communication, duplex communication between the consumers and the authority, electric authority. The electric supply to consumers made monitoring, analysis, control, communication within the supply chain. It improves efficiency, reduce the energy consumption and cost, maximize the transparency and reliability of the energy supply chain. That means that you know exactly what you are paying for, and you should, that received power should be reliable. We should not have any complaint about metering. We should not any complaint about the quality of power, etc. Now, features of the smart grid. First of all, it is a software-based automated control for transmission, distribution management, energy management, and decision support system. The automated outage management and self-filling quicker restoration after power problem. It's a very, very important feature of the smart grids. Self-filling. Reduce operation and management cost for utilities. Dynamic pricing mechanism with incentive to consumers to alter usage during different time of the day based on pricing signals. That means electricity department will allow the consumers to use the electricity when there is less load, and rate of electricity bill will become less. That means that this will be depending on that pricing dynamic depending on the load. If the load is high, you have to pay more. If the load is less, you have to pay reduced bill. Reduce peak demand. For that peak demand will be flattened and it will lower the electricity bill. And integration of customer-owned power generation system, including large-scale renewable energy system. It means the smart grid provides a feature by which if a consumer can produce or generate some electricity, the consumer could be individual, the consumer could be an industrial consumer, this consumer could be a society. If they are able to produce some electricity, they can, when they have excess power, they can transmit it to the grid, smart grid, so that they are contributors also. Real-time monitoring to track and manage energy usage through in-house displays in smart meters with power account and power management mobile app and web portals. This I will also show later on. And there is an opportunity to reduce and conserve electricity, very important. If you reduce consumption, naturally there will be consumption of electricity and security, as I mentioned. And after all, it will also improve the existing electrical infrastructure, which will add reliability, efficiency, economy, and environment. Now, power grids with distributed energy sources. Distributed energy resources means renewable energy power system like wind energy, biomass energy, or we talk about that tidal powers, etc. Solar energy. These are called DER, distributed energy source. Now the challenge for smart grid is to accommodate all of these resources within the grid. Since these DERs are subject to uncertainty, you don't know what will be the strength of the sunlight after 1 hour. Cloud may come. So that microgrid, we call it microgrid from the DER, may stop producing or produce less energy. That is unknown and uncertain. Anytime any calamity may happen, that will stop it. For a windmill, wind may come, may not come, you don't know. And when it will come, how much it will come, into what speed, that also you don't know. So they're full of uncertainty, and therefore you have to characterize all such uncertainties, make a model, robust model, so that this model can be integrated as a plan for the years, for any integration with the grids. This is also an important feature. So electrical power grid is more secure, reliable, sustainable, and efficient system when it becomes a smart grid. Now, so for infrastructure is concerned, we have the present infrastructure. As you see, the one is that power stations, distribution center to customer, transmission line with some monitoring, central monitoring, controlling system. Now, if you add the intelligence, telecommunication infrastructure with this, that ICT and other technologies, join them, it will become smart grid infrastructure, totality. Now it gets the infrastructure of the smart grid, which will combine everything. And if you don't have, it will be normal. Now I'll talk one by one. First is smart transmission. Synchronization of phases is very important. Synchro phases are developed IEEE standard 1344 or recently under developed IEEE standard 37.118 are the synchro phasers. They synchronizes the time synchronizes, and they measure the they have the PME unit, phasor measurement unit, after it is synchronized. For power system measured states, it may be voltage, current, or phase, and it should estimate within 20 to 40 milliseconds. And dynamic system conditions by a high resolution data with the rate of 25 to 50 samples per second sampling rate. It should have the ability to compare with time synchronized stamp data of voltage, current, etc. using global positioning system. You know, this DREs may be located in a remote sense where GPS is the only solution for time synchronization. On the GPS, you can locate everything. Now, very important is that wide area monitoring system, WAMS. What is means that you have smart system, you have smart computing system, you have smart network, but no network will function with that communication link. And because you are dealing with huge data infrastructure, you require huge bandwidth. The question is that who will transmit that bandwidth? Earlier, when I was in my student life, that time there was a subject you don't know nowadays, that is power line communication system, power line carrier communication, PLCC. Power line communication, that means using communication using that high tension line, but that is just for working, just for basic telephone purpose. We cannot provide for any data communication. So what is being done? The unique thing has been developed, which is known as OPGW, optical ground fiber. I hope that all of you know that nowadays that use bandwidth transmission is possible only if a fiber optic cable is provided. Now we cannot lay fiber optic cables for this for power supply, then cost of electricity will be very high. So what is being done, that if you have ever noticed any high tension line passing through some fields or roads, you will find that on the top of that wire, suppose 4 or 3 wires are passing, on top of that there is a single wire at the top, one wire. What is that? That is ground wire, because the ground wire is provided to absorb any hazard like lightning. Suppose the lightning comes, so because the topmost wire is fully grounded, so it will attract the lightning and make the entire lightning voltage grounded instantly without damaging the transmission lines. Now, what is being done? Like ACSR, where those who are electrical engineers, they may be knowing that aluminum conductor steel reinforced ACSR wires are that thick wires are being drawn for transmission lines. In a similar concept, instead of the core as a steel wire, here the core is put as an optical fiber, and it is surrounded by steel wires, protective wires, which is highly grounded, so that it will guard the transmission line for any natural calamity like lightning, as well as it will transmit high bandwidth communication signal through the core inside fiber core, inside fiber core. Now the thing is that the fiber itself is a non-conductor. So whether there if you carry 400 kilovolt or 200 kilovolt or 100 kilovolt, doesn't matter. There will be no electrical influence or induction problem because of the electrical lines, because the fiber optic cable itself is insulated. So by this fiber optic core cable takes charge of the communication infrastructure for wide area monitoring system, and I will see also act as a ground wire. High resolution time synchronized data useful for calculation monitoring. Dampers percentage measure the percentage of damping. Inter-area and local area oscillations are captured. It also measures sensitivities, the phase difference between the buses and transmission load, etc. Computational requirement in smart grid requires computational requirement in smart grid require very high computation power for connecting scattered resources over high-speed networks, management of highly efficient high-speed data network with huge data processing capacity and high quality of service requirement from the consumers. It also computational requirement is also for control of power network electrical grids to provide efficient and smooth management, monitoring and information. It's also used for exchange of distributed power networks with diverse widespread resources of power generations, electrical grid transformation, central generations transform into collaborative networks, which is nothing but to incorporate customer appliances and equipment and modern information devices in the distribution system. Complex computing using elaborate techniques also required computation, which is not achievable by the traditional technology. For that, you require this computing. Now, computational entities are load forecasting, demand side management, and dynamic pricing, which means the real-time pricing, time of use, and critical peak pricing. When the peak load, there will be pricing very high. So these are the entities we must think of, and there are three attributes of any power system: that generation, transmission, and distribution. And in case of generation, the specialty of smart grid is that it considers the renewables and microgrids, and for transmission, it considers the integration of those renewable energy sources, and it also considers the synchrophasers technology by placing properly the phase measurement units, power distribution centers, and data analytics. Smart grid distribution includes advanced metering infrastructure, outage management system, peak load management, power quality management, and electrical vehicles, which is also a part of the smart grid. Electric vehicles are supposed to be, connected to the smart electrical grids. Now, scalability property is another thing very important for smart grid. Depending on the demand, depending on the quality of service requirement, depending on the consumer type, it will automatically scale down or scale up its supply. For personal device, the quality of service and the performance will be different. And as you move on to the mainframe, its performance and quality service will be required more. And if you even move for enterprise or cluster grid, then also its performance will even more. And for global grid, it will be further more. Now, the scalability means that as per the required customer, you have to scale up or scale down the system automatically. That is scalability. And in this ladder, you find there are a lot of administrative barriers. For an individual, that's depending on individual decision only. When a group, there is something more complex. In a department, further complex. If it is a campus, complexity is more to state, national, and global. So all these are the part of scalability parameters. Now, smart grid initial version was just to have the intelligent meter, and in version 2, which is basically energy internet enabler, and consists of the advanced autonomous controls like distributed energy storage, distributed generation, flexible power architecture, autonomous control of loads. Last three are the part of the local low power grids or microgrids for DERs, actually, distributed energy sources, like solar, wind, etc. Now, some features of the microgrid: there should be a pilot microgrid system caters the requirement of about 30 to 35 households, which may produce nearly 100 kilowatt of power through multiple DERs. That means you may have, if you have windmills, you can put so many windmills to make a microgrid, and one of the microgrids in the territory will become pilot microgrid. It could be solar also, biomass also, it could be from battery also. Now, microgrid central controller, MGCC, is designed to regulate generation and load, and the eco-friendly microgrid is a need of the hour, because these microgrids are mostly located in remote places. Therefore, for example, it may be in hill area, it may be forest area, so that eco consciousness is very important there. So, and scalability and replicable model is needed to demonstrate an indigenous development capability matching the particular ecosystem in that DER. Smart grid has components. One is that phasor measurement, synchro phasor is required. One is smart meter, distributed generation. This could be wind power, this could be solar power, or anything else. And the information, the telecommunication part, the enabling technology part, and the data processing center headquarters, and some transmission capability, wireless transmission capability, data management, billing system. All these are the components of this smart grid. Now, I told earlier about the power management app. You see, in mobile, you may have an app with the symbol is the power, smart power. You can get. This is that smart meter reading. You may have smart safe house. That means you can control your electrical devices using the smartphone. You can switch on, switch off in any unwanted situation. Suppose there's a problem in your fridge or washing machine which is running, you can control that to on or off remote area. So smart automated devices and power account management, you know what is the bill coming and when the bill charge will be peak and when it will be cheaper rate, that also should be available to that. Then phasor measurement unit, the PMU detects abnormal waveform shapes, provides time synchronized sub-second level data, that means in millisecond level maybe. It can provide data. It shows dynamic behavior by observing high data rates and low latency from the computational procedures. Now, this is taken from one of the practical smart grid in India. You see, there is self-healing. You can see the cable. There is a simulated cable here. The overhead lines are there with all these bus bars, bush plugs, transformers, everything. If there is any problem, the operator just address that problem, and remotely they can control and make arrangements for self-healing of those faults. If there is any fault occurred, there is a provision that automatically it will be healed, automatically it will be repaired with necessary steps. Till certain, of course, to up to certain limit. After that, there will be human intervention will be required. Now, I was talking about the various features. One is the load forecasting model. It could be mathematical based computation models like auto recursive, moving average, and combination of both, or exponential moving, iterative, weighted mean square, multi-regression. These are required for demand side management, DSM, as I mentioned on the slide. And you can also use artificial intelligence AI models based on neural network, fuzzy logic, or expert system. All are available now for load forecasting. Now, another area is the energy management system. Energy management basically we do for residential, for a demand response program to be installed in the residential consumers and manage their power usage for reducing electricity bill. These models are required for grid, DERs, batteries, electric vehicles, and home appliances such as AC, fridge, geyser, vacuum cleaner, etc. to minimize the electricity cost in a smart home and find out operation modes of different loads. Just example, suppose you want to watch TV. Now you know that a serial will start at 7 p.m. So you cannot compromise. You have to switch on the TV at 7 p.m. But if you have a washing machine, instead of switching it on 11 a.m. in the morning when the officers will be there and load will be very high, that time in peak hours, if you run the washing machine, electric bill will be very, very high. What you can do, you can make the automatic choice. You can allow the washing machine to start because you don't require any particular time to start. You can start in the morning, early morning. You can start in the night when the load is less. How do you know? Because a smart meter will tell you when the load is low, when you are you are required to control your consumption, or when you can consume more because of the less tariff. That thing is available. So various optimization algorithms are available based on mixed integer linear programming formulation for energy management system. Now synchronization and security, there are synchronization is the presence of voltage unbalance and frequency variation due to increasing penetration of renewable energy resources into the grid. Now in the smart grid there will be too many. Now number of power stations are very, very limited in the country, but there are n numbers, thousands and thousands of numbers of the small microgrids throughout the region, forest, hilly places, coastal areas, and they are all can make together the system unbalanced, and the frequency they may vary. If the cost phi very high, value of phi will vary, then they will be totally unbalanced. So we have to take care of that synchronization of everything. So effective real-time state estimation is required for grid-connected power generation system for synchronization, and tracking the phase angle of the utility network is very, very important. Once you are able to track in real-time basis, then you can use synchrophasor for synchronization. Now, considering the security part, the cyber physical system, which was described yesterday by Professor J.K. Roy in his lecture, I will not talk much about that. It can use embedded intelligence and networking capacity for security. And we also put sensors to monitor various aspects of the grid, such as meter and voltage fluctuations as the input. Now, some benefits in terms of utility versus consumers. You can see the list for the utility is concerned. It will reduce cost, losses, then grid stability will increase, peak load can be managed easily, and you can integrate the renewable sources, self-healing as I mentioned, reduce capital and operational cost, increase employee safety, higher customer satisfaction, opportunities to leverage resources and enter new markets, and increase asset utilization. So for the consumers are concerned, the consumers can become prosumers. That means they can become producer and consumer. Suppose I am using electricity, I can put some solar panels on my roof. Or if we are living in a community, in the community level, we can have around 100 solar panels we can produce. Now we can, when we need more electricity, then definitely that will be insufficient. We have to take from the public electricity department. But when we have electricity surplus, we can upload it in the upstream grid. So they can become producer as well as consumer. Now, because there is a synchrophasor, phases are synchronized, the quality of power definitely is improved. It is user-friendly and transparent interference with utilities, and electric bill will be reduced to the consumers for shifting loads from peak to non-peak hours. There is an opportunity for the consumers to interact with the electricity market through home area network and smart meter connectivity. Similar opportunity to purchase energy from clean sources, further creating a demand for a shift from carbon-based to green economy. Suppose I want that I will use only green energy. I can give option that if is available some renewable energy, then only I use, otherwise I will not use. I will have option. Of course, the cost will be very high for that. Now, the way we have that internet, similarly we have power net, which involves the diverse and redundant path for the power to flow from distributed generation to use. The way the internet provides multiple paths, and based on the algorithm, the best, cheapest or most convenient path is selected. Similarly, for power transmission also, the cheapest, best, reliable route is selected for power transmission through that power net. The difference is that its control in the power net is residing in the autonomous distributed agent. Autonomous means who has the independent power to take decision. So those distributed systems can control, and they can involve a local approach for power interaction, contrary to the internet, which is centralized. Now, power is generated in distribution generators, usually from alternative or renewable energy sources. Now, once it is recorded, you need some buffering. The power buffer means when you need to upload some excess power, immediately that power has to match the electrical properties of the grid. So that buffer will be matching that. See, if the voltage is required to made higher, it will make the voltage as per with that, so that it can buffer. It is not wasted, that power. And when you put that excess power into the buffer, that has to be added to the system, the grid. For that, we need an energy buffer, which added to make variable sources dispatchable. That means it can be transmitted to the various locations through the buffer. That means two buffers, one for uploading, one for storing it. Now, talking about the Indian scenario, we produce about 60% of our power through thermal plants, hydel 22%, nuclear 3%, and through renewable 10%. The renewable is, of course, ever growing. This is, old data. I don't know exactly what you. And the users are, industry is the most user, 33%. Domestic is 22%, same as agriculture, whereas commercial 8% and others 10%. Now, this is the data I have received from Power Grid Corporation of India, and old data, of course. So, with this, India has 5 regional grids: north, south, east, west, and northeast another, because northeast the geographical characters is different, so separate grid is there for northeast. And so far the smart grid is concerned, we have 2 operational smart grids in India. One is in Dehradun and another is at Puducherry, erstwhile Pondicherry. And you see here is Smart Grid Control Center, PED means Puducherry. This is a photograph taken from that Puducherry center. And there are sanctioned 4 smart grid projects in India under National Smart Grid Mission. Like we have Education Mission, similarly we have Smart Grid Mission. One is in Chandigarh, one is in Ranchi, one is in Rourkela, and the 4th one is a distributed one comprising of 6 towns in Rajasthan. So these are underway, smart grid in India. Now, with the experience of 2 existing smart grids, some benefits have been achieved in India as per report of Smart Grid Corporation of India, Power Grid Corporation of India. One is that in those 2 places, that aggregated technical and commercial loss was reduced from 22% to 8.6%. So 14% reduction of loss is equivalent to 14% generation of electric power. So it's a great achievement. Then carbon reduction is about 87,000 tons per annum per year, and avoidable capacity 14 milliwatt. Clean energy development. Then it enables energy audit. Audit means that examining the accounting, that is audit. So we have the energy reports, that checking of those accounting is the auditing. The reduction in cost of billing, that also has been experienced in India. Remote load control, shifting of peak requirement to non-peak requirement, that is called peak shaving, and facilitate integration of large-scale renewable generation towards clean energy development. These are the benefits you see. But there are some issues also for large-scale integration. First, the intermittency. As I mentioned, the DERs are providing intermittent power. So that is a concern. And those intermittent also variable in nature and uncertain also. Right now it is there, but after 1 hour you don't know whether it will be there or not. And the plants are connected at remote and concentrated locations, maybe with weak transmission network. That's a problem. And renewable plants providing lesser grid support during system disturbances or exchanges. Suppose suddenly there is a demand for huge load. It is not possible for those microgrids to support that huge load, suddenly required. Then you have to depend on the traditional transmitting station, power generating stations. Now, question is that the three attributes I mentioned, the generation, transmission, and distribution. This generation requires the sources, advanced plan controls. Transmission requires the phase measuring unit, wide area automation, digital substation, compact optical sensor intelligence, and distribution systems require advanced metering, infrastructure, real-time management, etc. Now, the challenge is that how to integrate that. Integration means that how cooperate with each other. That's why there should be a huge, communication, huge data, huge infrastructure requirement. So how to get that? So how to store, handle, process, and analyze these enormous unorganized data. These data are unorganized and autonomous in nature. So how to that? How to store that, handle, process, and analyze? This can be done using cloud computing. It is nothing but using that internet to access someone else's software running on someone else's hardware in someone else's data center. We don't know what data center we are using, we don't know what hardware we are using, we don't know whose software we are using, but we are using. That is the concept of cloud computing. And it provides some application services, it provides various platforms, just like we take rented house. Similarly, we can rent some applications, rent platforms, or rent infrastructure for cloud computing. And there are various cloud computing organizations who provide this. The biggest is, of course, Amazon. We have SAP, IBM, Microsoft, Intercloud, Oracle, Rackspace, Google, etc. All of you know that the various clouds are available. You can take the clouds. Now these services, I have made a summary of these services. You can take the services as an infrastructure requirement. You can use services for your platform requirement, use the services for software or application requirement. And I have given the purpose and what are some detailed services available. And so for smart grid is concerned, you need infrastructure. Mostly we don't need as such unless the computational is there. But we need platform, we need software, all cloud is required. Infrastructure, so for computational part is concerned, we need infrastructure as well. Now, two types of commonly used clouds. One is public cloud, one is private cloud. Now, this public cloud means the resources are owned and operated by a third-party service provider and delivered over the internet. This is flexible, cheap, unlimited, scalable, frictionless consumption, and less worry, but with the fear of non-compliance rather than concrete requirement. Means that suppose you go to some restaurant for eating. Now the restaurant may offer you that if you are Bengali, they can supply the Bengali food. If you are Punjabi, they can supply Punjabi food. If you are Tamilian, they can supply South Indian or Tamilian food. And if they are Maharashtrian, they can put the way of their choice. If they can provide, that is a similar like public crowd. They have everything ready, but all are cooked in a same kitchen. That means they have a set, and you have to, adjust with their type. You will get your type of food, but with their infrastructure, with their system. That is the difficulty. What is private cloud is that if you are Bengali, if you go for a Bengali restaurant, you will get definitely that it is for the Bengali, all menus will be Bengali, and you can choose yourself based on your choice will be very much set from the available choices. So the thing is that this flexibility, the cheap is very important. That this is so cheap that if you have a private cloud, you have to need one data center, which is very, very costly, having data center. So having own data center is beyond thought of many companies. So private cloud is, normally it is very costly, I've heard, but in some cases, for example, defense, they cannot compromise anything with their security. So they cannot have any public cloud. They must have their own private cloud. For banking sector, they need the very secret financial transactions, users' information. They cannot allow to be floated in the public cloud, so they have private cloud. So like this, there are. But if you want for some specific purpose, you can hire some public cloud with the cheaper rate, much cheaper rate. So for the smart grid is concerned, the cloud deployment has some of the options. You can go for public cloud. You can go for it is private cloud. It should be private cloud. Then you have the community cloud, which is the multi-tenant platform. They can use the tenant for multiple persons for a platform. That is accessible only for a specific subset of customers. Community cloud gives much greater flexibility when it comes to industry-specific regulation and compliance. Suppose all the steel plants, they may have one community cloud because their type of requirement, type of security is common for all. Then your thermal power plants, electric supply, they can have community cloud. And IBM, Software, Google, they offer community cloud. Now, hybrid cloud is that suppose you have something to hide before the general public, very secret thing. You can just make two parts. The secret thing, you can have your small private cloud, and rest which are not that important in terms of security, you can put in public cloud for economy. So that is called hybrid cloud. The question is that what the smart grid will be doing. Smart grid cannot use any definitely private public cloud. They have to depend on either community or hybrid cloud. Now grid or cloud, basically both are the same concept. Both maximize the use of existing resources. Both economies of computing costs and both uses abstraction accessibility, they look similar. But in grid, one large task job is shared by multiple small task machines, whereas cloud offers users a variety of services without investing in the underway architecture, whether it is hardware, software, or network, from web hosting right down to workplace. Everything you can have. Now, when smart grid takes cloud computing, then one good thing happens, that the drawbacks of cloud computing is suppressed because it offers a very centralized service. It is suppressed by the grid company. Both are same, both are similar. So whatever infrastructure you need from the cloud, you can take whatever. You don't need for the public, or it is specific for your electricity purpose. You have your own grid, put their computer like a private grid, you can use it. So smart grid using cloud combination is a very effective of utilization the concept of cloud. Now, energy efficient home is the target for smart grid, one of the smart grid. That means you have multiple, as I mentioned, you have multiple devices in your home which can be controlled using your smartphone, and you can control. Now, this slide shows one estimate received from the Power Grid Corporation of India based on the experience of through smart grid, that suppose an urban area of 1 crore population, household population. Now, with the help of smart grid, they have seen that peak demand has been reduced by 12,000 megawatts annually. Energy consumption has been reduced by 30 billion units per annum. And 26 millions of tons of carbon dioxide reduction has been possible per annum. And reduction in infrastructural investment has been reduced by 1 lakh crore by the utility. Now, this figure, the average power saving through energy efficient per household, the peak demand reduction was in summer 1.2 kilowatt, in winter it is 2.5, nearly 2.5 kilowatt, and monthly consumption was reduced from 266 kilowatt to 199. Now, value of savings has been important. This varies. This is just for the sake of sample they have taken. They have it was calculated 10 years back. That time meter tariff was 4 rupees per unit, and it was found that a person can save 1,000 rupees per month during summer and about 800 rupees in winter, and annually you can save nearly 12,000 rupees, more than 11,000 rupees, and annual air pollution reduced now 2.6 tons. 2.6 tons per 1 crore population, it becomes 26 million tons total. 26 million tons. 1 crore population, and each one is 2.6 ton. Now, when you implement the smart grid, that time the project cost per house was around 35,000. Now, your annual saving is 11,000 something. So, you are getting payback within 3 years by saving electricity and other things. So that was the given data by the Power Grid Corporation of India. Now, demonstration of real life smart home. You have the Power Grid's smart home solutions in the control room. You have data concentrator unit. You have energy meter, RF module, load cutoff, and you have smart home, everything you can control. Now the question is that how to control and communicate with those devices. You have all these devices, they are dumb. They don't have any memory, they don't have any brain to do anything. How to do that? The answer is very easy, Internet of Things, which has been described yesterday in details by the two eminent speakers. I'll just repeat few of the things for the sake of continuity. Out of the 3 types of communications, that things to thing or machine to machine is our concern, that is the Internet of Things. A human to machine is like remote control, or human to human like email, chat, Skype. They are not our concern. Our concern is that thing to thing. Now, any object can be turned into a thing and may look as like an embedded system. Thing is generally can be a sensor, actuators, it can be microcontroller, communication unit, power supply, and usually powered by battery with limited resources, small in size, low cost device, and limited computing capability, and it cannot perform any complicated task, and power consumption is a very important issue for anything. And it can communicate, means the team working. It provides data link between the two nodes with the help of different communication, maybe copper, wireless, etc., etc. Various RF-based solutions you already has been discussed yesterday. It requires a network. Internet IoT requires a network for managing nodes, relaying data packets from source to destination, and networks are a distributed system, and they perform network related tasks only. And there are various type of networks. We mostly use sensor networks to manage WMN, manage, etc. like this. All are distributed. We have sensors and actuators. Sensors are input to sense the input, the signal, and actuators are based on that sense signal. They perform something. They alter the surrounding. They can produce light, heat, sound, etc. They can control motors, move objects. They can display images, and so on. So these are the inputs and outputs of the IoT. Now we use in the one of the area of this program is that talking about embedded system. Definitely embedded system, very important component in smart grid. It can integrate the measurements of electrical parameters. It can measure the power quality, very important thing. It can determine the power consumption in the grid. It can implement typical protection functions using of a digital relay, and integrate new system of protection. Whenever there is a new system coming to protection, it can be integrated. All are with the help of embedded system. The embedded system provides a platform to integrate innovative technologies of a processing, multifunctional, synchronization, and communication. Monitoring of high capacity computing for field area acquisition and multifunction processes have also application for embedded system. It is also applicable for signals to detect, identify, and if possible, locate non-stationary disturbance using advanced processing techniques. And embedded system is very much used in energy management in all micro smart grids. Now, this perhaps the IoT things connecting things, that for example, that in a just automobile, it will have lot of sensors at a mobile node and a mobile router. If it is lacking any oil is about to be exhausted, it will give an alarm, and it will put it load to nearest petrol pump. Similarly, if there is a problem in the system, any mechanical or electrical or any other problem arises, it can get an alarm so that it can lead to nearest service center, and all are possible using that internet Wi-Fi. This is the IoT thing. I just reminding you have already perhaps learned yesterday. And wireless sensor network using the sync node, this also has been discussed yesterday. I'm not going further. Now, so for the smart grid and IoT solutions concerned, that the operating technology means that technology which are existing for existing grid. And what you do, you add or integrate information technology on it. So that integration is very important. This is called IT OT integration, from field to control center to enterprise, everywhere. Overlaying of information and communication technology on the operating technology of the existing grids. For example, smart grid using a smart generator to produce efficient power, we get smart energy. For energy services provider, bridging supply and demand, we get smart data center. For renewable operator, making renewable dispatchable, it gets smart integration. So all these are possible with the IoT solutions. Now this is the slide of the vision. This is from Power Grid Corporation of India. You see the logo. They have shown, you see a typical smart gate city, how it looks, it will have, say, smart transport system that electrical vehicles maybe have, the smart control system, e-governance. You see that renewable generators here, a lot of things, and you have e-distribution. The distribution is e-distribution. You see that. Then you have smart buildings using the smart homes. It's all smart homes. The e-medical, the hospital, written hospital, e-medical center. Everything diagnosis, doctor can from the remote can check the status of the patient, and these are the microgrids spread over. This is the vision of a smart grid, all integrated. Now the technical question comes, that is reliability. The reliability of smart grid is that resource adequacy and operational security issues for power grid planning and operations. Then the reliability depends on an ideal mix of resources such as renewable, demand response, and storage. You know, we must know that what is the storage to the buffer, what the energy buffer is talking about, what is the demand response curve is showing, what are the renewables available, what is the current status, and whether there any threat for the ability of that. That should be the consideration of the reliability. Some reliability issues are that adequacy in the improvement of electric and power and congestion prevention in large scale presence of large green energy. The green energy is the source of the crux of the problem, so we have to manage that. And partially replacement of large and centralized resources by efficient and renewable distributed generation, DGs. That is also reliability. Increasing utilization of renewable DRs, optimal and reliable operation of distribution networks by controlling the new uncertainties with the power system operations, like COVID situation, and you don't know what will do. Flexibility in the demand side of power system can improve the power system resilience. They can protect from any hazards. Now, security issues in the smart grid, we are coming towards end. This is the last issue of this. The attackers may disrupt the security of smart grid systems with techniques such as denial of service attack, random attack, data injection attack, by exploiting the communication infrastructure among the sensors, actuators, and the control system. They can infiltrate with any other thing and can attack with these things. So we need a robust security framework for smart grid. And what is needed? We use that Kalman filter, very common filter for smart grid, and a lot of papers you will find in the literatures about the various types of Kalman filters, modifications, and Euclidean detector. These are some of the common tools. They are used to estimate a series of predictor variables that can detect system faults or attacks due to denial of service attack, short-term attack, or long-term random attacks, or false data injection attacks. That means data has not been injected but is giving that false injection attack. So like this, we have to take the security concerns. Now, if you are a faculty or a researcher, or if a student want to do some project, if they want to learn more and more in smart grid, there are various areas. I have given some of the salient areas of like load forecasting and model using artificial intelligence, mathematical model you can use for the smart grid. Demand response and management in smart grid is an area, very important area. Smart grids, energy hubs and storage models. Then residential energy management in smart grid is already there, but there is continuous improvement in that. Mathematical modeling of smart grid interactions, I mentioned smart grid, microgrid models you can make, wide area smart grid networks you can think of, the communication system you can think of. You can think of IoT applications in smart grid buildings, and security issues and Kalman filter. You can work on that. And of course, smart grid environment. Environment is very, very important concept which is leaping in bounds in the current years because we are dependent on the local environment for those DRs like forest, coastal areas, etc. We have to keep that environment intact. So I have some concluding remarks. I think within time, no? Okay. Growing usage, demand for reliability, security, efficiency, energy sustainability, and enhanced complexity of power grid compression leads to smarter grids. That means if you have grids, go for smart grids. If you have smart grid already, go for smarter grids. Because that is a dynamic, the usage is dynamic, reliability is dynamic, see everything, more and more demand, more and more reliability, for security, reliability is going on. If you, so this improvement is a continuous process. The environmental issues are initiating a quantum leap in harnessing ICT and other enabling technologies. Could you imagine the COVID situation? Now there is a lot of impact in smart vehicles. If you there is no communication, how can you reach that? Suppose there are smart grids in Sikkim, northeast. Uh, uh, so somebody, the engineers, in case they have to reach, there is no communication, everything is stalled. How to manage that? How remotely you can manage that? Then the thing is that because of COVID situation, there is some that you have to maintain some distance or some precautions you have to need. Whether you are prepared to do that. Now today there is COVID, tomorrow something new come. Whether you are prepared to face any environmental issues, whether it is that spread of some disease or anything else. And energy objectives are four. We have to think always, whatever you do, that energy efficiency and conservation is a main concept. Then energy, what you sell should be competitive, it should be secure, and it should emit less carbon. And it should optimize with these smart technologies. And transport sector decarbonization using grid connectivity, using IoT is very, very important, and it is undergoing also. The cost of that electric vehicle is still higher because of this problem. We hope that in future this will be, there is a lot of improvement and cost of electric vehicles will be lower like this. Now making the grid infrastructure smart with meters, connected homes and buildings become now transparent. You can, everybody, there is no unbelief. Or this year, this month, my electric bill is so high, I cannot believe something wrong with that. There is no such case. It will be all transparent. And it is estimated by 2000 this year that there will be about 50 billion devices across a variety of industries which will be connected to the internet and peer-to-peer connections as well as smart grid infrastructure networks. Through the IoT, consumers, manufacturers, and utility providers will uncover new way to manage devices and ultimately conserve resources and save money by using smart meters, home gateways, smart plugs, and connected appliances. And we move towards green energy and smart city for our future generation. With this, I hope that future network will be more stringent, we will have more stringent security, and there's no issue of privacy, and we'll have a better power source. So thank you very much for all your patience hearing, and if you have any question, then I am ready to answer.
Thank you very much, sir, for your very enlightening, very particular slides. Each and every slides are very relevant with the topic of smart grid with enabled technologies for distributed power generation system. I would request participants to put their questions, if any. May participants ask question? Sir, may I ask one? If not, uh, energy actually sir, is associated with the development of smart advancement
Can
of.
you give in chat box? I think that will be better.
Yes,
The
sir.
can be given in chat box. I
Yes,
think.
sir. Yes, sir.
Because there may be some problem with the audio.
Yes, sir. Yes, sir.
Better.
So while sir is typing the questions, so any participant, if they want to ask questions verbally, they can do that.
One question. I'm
Yes, sir.
sorry that HTLS conductor is smart grid that is not known to me. Normally, what see conductors in normally we use that ACSR. Whether smart grid will have any effect of that, that is not concerned. I don't know whether the conductor types could be made difference. What we do, we have existing infrastructure. Whatever we have in existing, we will use that. Not we cannot throw it out. Only what we do is we add some ICT based infrastructure in addition to that. We add the control room, which is extremely computerized. We add some telecommunication network using the fiber optic cable. So the conductor part, I think it is not a question of smart grid. Smart grid is compatible to whatever you use. That is my idea. In particular, whether HTLS conductor is having anything or not, that answer is not known to me, sir.
Any other question, please?
Can smart meter indicates the reactive power of the consumer? Yes, there is option. Actually, the reactive power you can, that is between the mutual. I told you there is a digital platform for the utility and the consumers. If the consumers want to know the reactive power, definitely they can get it. Because of the mass, the common mass, they don't have any issue with the reactive power. So they don't bother. But if you are a technical person, if you want to know, there is option in the smart meter, you can do that. Everything is transparent. Main concern is the micro grid, nano grid, mini grid, whatever you call. That integration and make everything smart. Is India is very proactive with green energy integration in grid with respect to developed countries? I'm sorry that I don't think so, because India is not that proactive. Now, I mean, some steps are taken because the initial investment for this is not only investment very large, the technical know-how is very important. For example, I need some infrastructure. The decision whether I need the infrastructure from the community cloud or I should, I mean, have it my own private cloud. And depending on that, the government investment will be dependent. So these are some complex issues. For example, a lot of paperwork, lot of years, government has four projects. So whereas in Europe, they are using huge because they have that their terrain is very fit for smart grid, windmill, etc., etc. And we are compared to that Europe particularly, we are lagging behind. Develop particularly Europe. America, we also develop. We are lagging. Definitely, we are lagging. But we have a lot of resources. In Northeast, a lot of works are going on. And area and the coastal area. Puducherry has been taken that wind power, and Dehradun is taken for solar, etc. Others. And
so is nicely answered and is a current view of Indian grid advancement. So thank you very much, sir. We are not finding any other questions, but yes, sir. Another one is coming.
can you illuminate us on IET in smart grids? IET, what do you mean by IET? Can you what do you mean by IET? IET, a lot of abbreviations.
Intelligent electronic technology.
Sorry?
Intelligent electronic technologies.
Can you write it?
Actually,
I cannot hear it. No, it is so noisy. Intelligent electronic. Oh, acha, acha. Intelligent electronic technology. We are using that. We are using embedded system. What is that? That's a part of intelligent electronic technology. So we are using embedded system. We are using all intelligence system. See, it is very difficult. For example, they predict the nature. Then you have to have a very complex algorithm. And according to that algorithm, you have to, that I mentioned in one of the slides, that is that construction, grid application construction. That you have to make that intelligent electronic technology, that is what you mean. They're using that embedded system, that what could be the chain reaction of one calamity. If something happens, what could be the next thing? That we have to predict. Accordingly, you keep your devices ready to accept that and manage the situation, so that grid is not at stake. It is never falling out of phase, or there is no other total interruption in the phase.
Yes.
So it is very IET, what you refer, is very much used.
Thank you, sir, for answer question and suggestions. And I would take the privilege to just present you memento in terms of this presentation to you. We are going to present it by screen sharing, sir. Sir, please hold for a while. Yes.
I cannot see that.
Yes, is I think view is a road. Sir, is it visible now, sir?
No, not visible to me. Actually,
Sir,
beginning I was facing this problem.
Okay,
That,
okay. Now others window it is coming only.
Okay, sir. Okay, I am presenting. I am here. Okay.
but I cannot see it. Anyway, thank you for
No, no.
your presenting.
Sir, please hold on for a while. I am presenting now.
Some problem maybe with my system.
Sir,
Sir, is it coming?
Head HOD presenting like that, but nothing is displaying. I cannot see anybody. In fact, just maybe whether there is some.
Okay, sir, we will send you to you by mail also.
Now I can see. I changed the layout.
Okay.
Yes. Can you see me actually?
Yes, sir. Yes,
Visible or? Huh?
is visible. Yes.
Your excellent mentor. I'm really thankful.
Thank you, sir. We'll send the same to you over email.
Okay, thank you very much. Yeah. Was it properly audible? Because I don't know.
Yes, audible, sir. Entire session
I
was
don't
clear.
have a special device. Simple.
Yes, both and voice was clear. Both audio
Why?
and video are clear.
Clear. Okay, okay.
Yes, sir.
You are Bishwajit Haldar.
Yes, sir. Myself faculty of this department.
Acha, 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 acha. Okay. Thank you.
Okay, sir. Sir, your very important message about this PMU and these reductions of carbon monoxide with the investigation. There's so many new things been found. Sir, in future also, I expect you come and join our
I'm
sessions.
coming immediately.
It will be very helpful for our participants and us also. Both.
Our head of the department from EC department has joined. Would you like to say a
Yes,
few
yes.
words, sir?
I can say something. But I am in time, just 1 o'clock.
Sir, actually, I was there from 11:45 and muting my audio and video, and I am also following your lecture, but this topic is not understand to me because I am not for the smart grid and so smart on the grid. So for this reason, I just gather some information from your lecture. So, sir, it will be absolutely benefited to me. Thank you, sir.
Okay, thank you.
Thank you, sir. Thank you to all. And thank you, Professor Mukhopadhyay, because we have touched upon the most relevant topic of electrical engineering. Thank you, Dr. Haldar, and to all the participants who stayed with us. We will join again at 2 p.m. sharp for another lecture session from Professor Devash Chatterjee of Bharatpur University.
Thank you. Thank you very much.
Okay.
Okay, all of you, thank you very much.
Thank you, sir.
অর্কেন্দু স্যার আছেন নাকি? গুড আফটারনুন অর্কেন্দু স্যার। অর্কেন্দু স্যার আছেন নাকি?
Hello, Dr. Paul. I think you are on the road. Can you please mute yourself?
রুম অ্যালোকেট করা থাকে প্রতিটা পরীক্ষার একেবারে রোল নাম্বার দেওয়া হয় রোল নাম্বার এক থেকে এত
Hello, Dr. Paul. Hello?
Yes, madam.
Can you please mute? Sir, you are on the road. Please mute yourself.
Phobos.
Welcome, sir. Good afternoon. Hello, sir. Please unmute yourself.
Good afternoon, actually. Sorry. So it was
Okay.
what happened? I
Okay,
don't
sir.
know.
So
There
finally,
are,
there. Okay, sir. No issue. So I'm just because we are slightly ahead of the schedule, so I'm just starting. So let me take the privilege of introducing Professor Debashish Chatterjee to all the participants here. So I will just take a moment. Professor Chatterjee is presently associated with the Electrical Engineering Department of Jadavpur University. He has completed his graduation from Jadavpur University and Masters from IIT Kharagpur and PhD from Jadavpur University. Before becoming a professor, he has served several industries like Philips India, Crompton Graves, National Radio and Electronics Company Limited. He has specialized in electrical machines, power electronics, and drives. His research area involves speed sensorless control of induction motor, sensorless control of induction generators, microgrid control, efficiency optimization of electric drive system, electric vehicular drive, development of solar and wind hybrid system, and synchronization of the same to the grid. He has published more than 100 research papers in journals and conferences. So now I would request Professor Chatterjee to go ahead with his session. Now the platform is all yours, sir.
okay. Thank you. So first of all, congratulate your effort to arrange such a seminar under these circumstances, and that will, I think, that is bound to help the participants in the way that they will be able to come to know regarding the research work that has been carried out by many of the, eminent persons, and then they can also, solve some of their own problems, and they can do some future work. So this kind of programs always help. So okay, so again, thank you all, and I'm going to the presentation status. Okay. So now, is this visible to you? Hello?
Yes, sir. Yes, sir. It is fully visible. Yes, sir. It is fully visible.
And also, I am audible to you also.
Yes, yes, sir. Yes, sir. You are fully audible and it is visible. The slides are fully visible.
Okay. So thank you. So I am starting. So today, in the scenario of, say, power crisis, rather, so we are thinking, we not only we means actually various persons who are doing some research work and some industrial R&D sectors also, and they are thinking actually to somewhat, there are two issues nowadays coming. One of first thing is that energy demand is increasing, as because we are going into more and more mechanization, and various kinds of, say, even at home also you will find electrical gadgets, they are getting introduced. So therefore, and then when they're manufactured, so that industries also, they need power, right? So therefore, actually, the energy demand is increasing, very rapidly these days. And the second issue is that when you have to meet the demand, the generation of electricity has to be also increased. Now, the generation of electricity, as you all know, there are major ways actually through the conventional fossil fuel fossil fuel as the raw material. Okay. So in this case, so when you use fossil fuel, so there are different, you can say that there are different hazardous effects that can come into play. First of all, the fossil fuel is a limited stock. So if we exhaust it to the more and more extent, so therefore, I mean, at some time will arise, where actually we find that there are no fossil fuel remaining. So this is one issue. Second issue is that the fossil fuels are usually burnt to generate heat, and then heat is converted to electricity in major cases. So therefore, this heat which is burnt is not fully utilized to generate electricity. So there is some efficiency factor. So major heat is released. Not major, I mean a good amount of heat is released into the nature. So that actually increases the atmospheric temperature. And secondly, when there is a burning of fuel, so there are different hazardous gases that can come out, that are coming out, and that are again mixing in the environmental say air, and then that pollutes it, and ultimately it is harming us. So then the second technology is that people try to think that how to introduce the other sources which do not have such emissions, which do not introduce so much of heat, right? So the ways are actually the the renewable sources, or you can say green sources. Now again, when you generate a lot of power through green sources, the problem is that as you see that fossil fuel, we can make a stock of it. Okay, we can make tons of coals, or you can say petroleums, that can be reserved, and as and when it is required, you can utilize it. But the natural energy that we are using, mainly in the form of wind and PV, you see, that is a huge stock, although, but you cannot have it at your own will. That means when you need it, it is not necessarily that you will get that energy. And there is no question of stocking it also. Okay. So therefore, actually, came different technologies, like how to utilize with such uncertain nature, utilize these sources with such uncertain natures. Now the concept of different say smart grid, and then micro grid and all came, and then we are also doing some lot of research on that. So here we will be starting the discussion on this way. Actually, the smart grid load management, and to some extent that non-intrusive load monitoring, and the idea of regarding load, and the modern technique with IoT and renewable sources, means renewable sources as an energy source, and then utilization of some kind of IoT to manage the loads in a smart grid. Okay, so this is the topic of the lecture, and you should be a little bit more theoretical rather than I mean logical one, because you will not find a lot of mathematical equations coming and getting solved, and it becomes very transparent to you. So mostly the lecture will be actually a little bit of theoretical in nature, which are not really implemented these days, which are going to get implemented in future, and some part is implemented. Okay, now we come to the point. Now the structure, if you see, I was talking about the grid. So what is a grid? So grid is, if you see, normally is nothing but a connection point we see. Okay, and this connection point may not be a single point. It can be a long line, and then all say gadgets can be connected. The gadgets could be a generating gadget and a consuming gadget also. Electricity generating gadget and electricity consuming gadget. Now if you see the conventional grid system, it's an interconnected network for delivering electricity from suppliers to consumers, right? That's we are saying. And consists of generating stations that produce electrical power. That is quite evident that I was talking. And then now the generating stations, as we see, they are not located near the load centers because of several reasons I was talking about. Because these generating stations normally emit a lot of gases, emit a lot of heats, and also it may so happen that your fuels which you require to generate the energy will not be available at the place of load. So therefore a lot of transportation can physical transportation, like physical transportation of say the fuels has to take place, and that can increase the generating cost also. So therefore, they are located at some suitable locations, meeting those criteria as I was talking about. So therefore, the generated electricity has to be transmitted to the load centers, right? So then the middle green point, so high voltage transmission lines that are required, that is to carry power from distant sources to the demand centers. And then again, as the the power has reached the demand center, it will not so happen that the power is concentrated at a single point. So the power can be concentrated over a say a circle of say 10-kilometer radius, let us say, or 5-kilometer radius, right? Now in this fashion, so there should be some distribution lines. So therefore, this is known as distribution system, electricity distribution system, right? To the individual customers, maybe industrial, maybe residential. So this is what your structure of the main grid. Now this is actually a pictorial view of it. This is the generating station. This is the transmitting network, and these are all compensating units in between. And then this is the distribution network and the loads, right? So this is what different transmission levels and all that you all know. Now then came the concept of microgrid. Then came the concept of microgrid. Normally, this grid I was talking about, which is the main grid, large grid. I mean, the sources of large power, they are connected to it. Maybe a single unit of 500 megawatt, 750 megawatt, like that. Even 210 megawatt, 100 megawatt, big units, they are connected. Now, a microgrid, actually, as you see by name, it is micro and grid. That means it's a quite smaller version of the main grid. Now, if you see what are the sources then that will be connected, a microgrid is a grid where we normally connect the distributed generated sources, distributed generation sources, like the ones which is the ones which is generated through the renewable sources, right? Now, if you by definition sees the small scale generated units to a grid connected to distributed, I mean small scale generation units, they are known as distributed generation units, that I will be coming. And a microgrid is entirely a DG based grid that contain both generators and loads. So this is what I was trying to explain, that the main grid actually will be having a source of very large capacity, and instead the microgrids will have sources of smaller capacities, and preferably they will be renewable in nature, and they can be of smaller capacities. And this microgrid, actually, this will supply some localized loads that are in the vicinity of this grid, right? Now, what happens? Now, as I was talking about, that the renewable sources, they are not predictable in nature. So today, if wind is there, tomorrow it might not be there. I mean, tomorrow, today is there is sunshine, so 1 hour later there can be clouds, so the sunshine can go away. And sunshine, there is another issue, one mandatorily, in the night time there is no sunshine. So therefore, as the load can be of different natures, that means the timing of the load, the timing of the load demand is not known. It is up to the consumer. So the supply companies has to be ready to supply them at any point of time. So therefore, it may so happen that this microgrid will not be able to cater to the loads throughout the 24 hours, okay, of a day. Now, therefore, this grid has to be connected, microgrid has to be connected to main grid, okay. Now, this connected operation is one which is known as grid connected operation, and there is, it may so happen that it might not be connected to the main grid. There could be different reasons. First reason could be the main grid having no power. Second reason could be main grid having some faults. So it can be gone to a disconnected mode, and technically this is known as islanded mode. So this grid can operate both in grid connected and islanded mode operation. So that we'll learn later and later. I think not from this lecture, I will not be going into that one. So in an islanded mode, only the DGs are connected to the microgrid to supply the loads. So there could be some adjustment of frequencies, voltages, and power distributions, or other power sharing between the loads when it is in grid connected or in grid isolated mode. So now this is the structure that you are all, acquainted with. There are different sources and loads. Now, I'll just give you a general structure of the distributed energy sources. Now, distributed energy sources, as I was telling, that we have a source mainly non-conventional in nature or mainly green nature source, and this is this one. So it can be wind, it can be PV, it can be tidal, it can be say other say fuel cell or anything. Okay. Now this source, as they are not predictable, so then the generated power is also not predictable and the power quality is also not predictable. Power quality means at least for AC, voltage and frequency, and
Hello,
for DC,
sir.
voltage.
Hello.
Hello.
Hello, sir. Sorry to interrupt you.
Huh.
Slides are not changing.
Is it?
Sir, yes.
This is changed.
I'm finding the same title slide for a long time.
Oh,
That is
is
why,
it?
sir, I'm asking you.
Okay, again I am going. Okay, again I am
Yes, sir.
checking.
And you please switch on to the presentation mode.
No. I'm presentation mode was there actually. Is it coming?
It's not showing in the screen. I don't know about others whether they can
Just please
see the
confirm. So then I
presentation
will
mode.
adjust. I will see what is happening.
I don't know. What about the participants? You may reply.
Sir, you please press F5, so it will be full screen.
I have pressed F5 only. It is in F5. Oh, sorry, you could have pointed out earlier. So I have already crossed 5-6 slides. So
it's okay, sir. It's
okay,
okay.
I'm re-entering. Okay, I'm re-entering. Is it coming?
Sir, it is the title slide. It is coming.
But full screen?
But no, sir. No.
It is not.
No.
How it is? What is happening?
So you select the window in which your PPT is there.
I'm selecting.
So is your PPT open? Then you select that window.
Is it okay?
It's coming.
No, it is
And
coming. It's not in full screen.
no,
Uh,
not yet. So you
now,
check
is
if
it
the
coming?
slides are changing. So you
Is
check
it
if the slides are changing, sir, that you check.
changing?
No,
Not yet.
no.
Are, how can it be? Uh, changing.
Yes, sir. It is now changing. It is now changing,
Actually,
but it is not full slide,
uh,
full screen.
full screen mode, it is not changing. Why? I do not know.
Oh.
Now it is changing.
Please go to the next slide. It is the title slide.
No, no, it is not changing then.
No, no, it is not changing. Now it is
Yes.
changing.
So
Now
then
it is changing.
please bear with me. So I don't know why it is happening.
Sir, sir,
I'm
there is
increasing the thing. Is it, this is okay?
no, sir.
This is
There,
fine for you?
no, no, sir. But there is an option of slideshow, full screen slideshow.
Full screen. I have gone there only.
Press F5, sir. Press F5. Function key F5.
Entire screen.
Go enter screen. Sir, are you presenting?
Just I'm giving again. Now is it coming?
Yes, sir, it is coming.
It
Full
is
screen
coming.
or not full screen? Slide changing.
Not yet. Not yet come. It is not yet come.
Sir,
Slides are not changing.
Sir, your slide is not visible.
I don't know what is happening.
Sir, you stop your presentation, sir, please. Sir, you please stop your presentation.
I'm stopping.
Sir, we present now and then go full window or a window.
Your entire screen.
No, sir. Below that, a window is option is there.
A window is there.
Yes, sir. Click the a window.
Then this PowerPoint presentation is coming. Entire screen.
No, below entire screen there is another option, a window.
Below entire screen there is no other option. This is load monitor PowerPoint presentation. Now it shows this one. So when I click this, it gives you just a minute. This is okay.
Then, sir, go to your enter screen.
Something has come.
Yes, sir. Now coming. And, sir, please press F5.
Now I'm pressing F5. F5. So, full screen.
No, sir.
Hello, sir. Hello, sir. You go down, and there is an option for full screen rather than F5. F5 may not work if it is PowerPoint 2010.
That also I have given. That also I have
Yes,
given.
yes,
Slide
yes.
show. This one. Don't know what is happening.
Okay, sir. Then you continue by changing the slides. Then I think
The slides are changing. The slides are changing.
Yes, sir. Yes, sir. It is now changing.
Then I continue like this. Otherwise, it is just wasting of time.
Okay, sir.
This is changing. Now you are able to see the next page.
Yes, sir. You please scroll down. Then We can check once again.
This is the first page. Right. Next page.
No, it is, sir. It is
Right.
not coming. No.
Oh. Earlier it was started coming. Now is this changing? Hello.
Sir, please go to the next slide. Let us see.
I've gone to the next
Yes.
slide.
Yes, it has changed. Then you please go to the next slide. Yes, sir. It is changing now. You can continue.
Okay, I am continuing. Huh?
Yes, sir. Yes, sir.
Okay, here I was actually there. So I am continuing from here. Okay. Or I have to repeat earlier one. So earlier one is just I have explained. So what are the things? Okay. So should I continue now? Hello.
Please continue, sir.
Okay, all right. So the general structure for the distributed energy sources is this. So as I was talking about, the distributed sources, they actually convert electricity. They actually convert electricity from the renewable sources. Okay, they convert electricity from the renewable sources, and which are actually unpredictable in nature. So at the same time, when the source is unpredictable, the generated power is also having inconsistency. Like, say, if it is a DC power, the voltage might change abruptly or slowly, or if it is an AC power, both voltage and frequency can change. So therefore, in order to cope up with this kind of power and to make this utilizable, so there is one interface. So there's a power electronic interface. So that actually stabilizes the voltage or the output power into an usable one, maybe a constant voltage, constant frequency, or maybe a constant voltage with a frequency that is suitable for the PCC, right? So this way, and accordingly, in order to control that, there are certain associated accessories like measurement system and control and protection system. So this gives you a block diagram for the general block diagram for any distributed energy source, right? So now this source actually this has become possible only because of the modern day power electronic technology which is available. Because see, when there is a voltage instability, so there are some switching and along with some control techniques. So that is that can be feasible with the help of power electronic, say, controllers as well as processors. Introduction as well as I mean processors with high computational ability, availability of processors with high computational ability. Okay, so then this evolution actually is due to the development of fast semiconductor switches and introduction of real-time controllers. So this is actually the general outline for the microgrid, I mean DG-based microgrid system, right? Now the renewable sources, as I was talking about, can be of this kind of nature, or maybe even something more than that, like wind, solar photovoltaic, micro hydro, tidal, geothermal, fuel cell, and biomass, out of which the first three are the major players. Now they are having the major share among the all renewable energy sources, right? So now again another thing is coming, which is a smart grid. Now we are entering into the system. So now the microgrid, firstly we started our discussion with a normal grid which have a source of large in nature, conventional sources usually, And then there's a smaller version known as microgrid, and the sources of the microgrid will be actually the distributed generation sources, and the input is from the renewable power. And then this grid can be connected with the main grid in order to have power exchange. When there is a excess power, it can also feed it to the main grid. When there is a shortage of power, it can get the power, extra power from the extra requirement of power from the main grid. So this is another mode. And then these two grids are actually you can say they are not intelligent in nature. So nowadays, actually, as I was talking about, there are various types of loads that are getting introduced. So some loads are sensitive, some loads are not sensitive, some loads are actually they can be made on at fixed point of time. Means I mean it's a requirement. Supposing you want to cook, so the cooking will be always in the morning and in the evening, right? Or in the morning and the evening. But suppose some loads there can be shifted, that can be shifted also, like a pump. So you can shift your pump cycle, water cycle. Okay, so there are, supposing ironing, you want to iron something, so that also can be shifted. So those things, some loads are shiftable loads. So now there is no intelligence that is there in the above, in the other two grids I was talking about the main grid and the microgrid. But then there is a third type of thought that has come, which will be able to manage both from the load side and from the source side. That is known as smart grid. Now, the smart grid concept, actually, if you say, it combines a number of technologies and end user solutions and addresses a number of policy and regulatory drivers. So now, if you see, smart grid means now there will be high-end technology. It does not have a clear definition. So second line is actually more important for you. A smart grid, actually till now you cannot define that this is known as smart grid. So there are, you can say there are some added features like say protection, self-healing, intelligence, and then information exchange, etc. So these are the general features of a smart grid. So then if it does not have a clear definition, so the smart grid should have certain, say, criteria like intelligence to integrate actions of the connected users and generators. Like, sorry, intelligence to integrate the actions of the connected users and generators. Now, what is that? Now, that I was talking about. Say, supposing you have a pump, so then it can tell you that say this time if your pump is on, then it will be helpful for the generating unit, because normally if you see the peak load appears at the time of say evening, say 5 to 8 or something like that, and sometimes even in the midday also, when all the offices are there, all lights, fans are on, and etc. So then during the peak load period, so if you switch on the other loads, actually your plant load factor can deteriorate if it is not properly designed. So these things actually can be I mean interactable, I mean can be available with this smart grid system. So the generator and the users, they can be actually aware, they can be given the information. Now, secondly, it should efficiently deliver sustainable, economic, and secure electric supply. So then, sustainable and economic, you know. What is secure electricity supply? Now, secure means actually, say, all the grids, all the generating units, if you see, say normally these conventional generating units, they are run on the basis of some predicted load cycle. That means if you see, even if I run a thermal power, so this moment if the load increases to say by 100 megawatt, so immediately we cannot increase the generation to 100 megawatt. So there are certain procedures. So the governor opening, fuel injection, and all that takes around half an hour, right? So therefore, some preparations are required, right? So now, if it so happens that someone has hacked your supply, and then this thing operates on, say, hourly basis data, say the next hour what will be your load that is predicted, and someone hacks and gives you a wrong information, and you operate at a very low load, but the demand will be very high. So what happens? Naturally, frequency will fall, and there will be catastrophic. So therefore, this should be actually secure. That means no one can actually enter into it except except certain users who are allowed, right? And it should use, and say thirdly, it should use digital technology to improve reliability, security, and efficiency. And normally, this is the latest technology, that is why it has been done. And it should have appropriate economic storage system also. Now, smart grid should have storage system. Why economic storage system? Now again, this term is actually explanatory. It has to be explained. Now, like supposing you have a small grid of say 100 kilowatt, right? That you have converted into a smart one, and you have some loads which are actually which cannot be interrupted, and some loads even they can be interrupted and there is no problem. So then, if you design your battery system entirely for 100 kilowatt, right? So then ultimately what happens? Your energy pricing, your cost per unit will rise. So therefore, you should be judiciously choosing your storage system so that your overall price does not increase. At the same time, you will be able to supply the critical loads during the failure of conventional powers, or during the failure of power from the other sources. Okay, so those things are there. Those things should be there in a smart grid system. Now, why smart grid? It is a better situational awareness and operator assistance that I was talking about. Now, autonomous control actions that I am also already trying to tell you. Now, what is autonomous control action? Means, supposing, say you have introduced a load which is generating a lot of harmonics. So that harmonics, that always what you see, that harmonic injection should be within certain limit and all, unless and until it is there. So there are some regulations that has been imposed. So then, supposing you switch on a load which generates a lot of harmonics into the. So is it okay? I mean, is it visible to you? Hello?
No.
Is it visible? So then,
sir, it is visible. Yes, it is
Hello?
visible.
Okay,
yes,
okay,
it
all
is
right.
visible.
Okay, all right. So then, actually, autonomous control actions, that means automatically it will be alarming you. So there some load is connected which is injecting harmonics, right? Now, efficiency enhancement means actually overall efficiency for the total connected devices has to be increased, and energy efficiency should be higher. That's because of cycle shifting and usage and all. Now, integration of renewable sources, that have to be also there. Now, improved market efficiency through innovative solutions for product types. So that will be explained later on. So higher quality of service. That means it will be giving you a voltage, stabilized voltage and stabilized frequency without any interruption. So normally this is what is the motto. Now, structure conventional grid has been discussed. Now, why this smaller grids to be converted to smart grid? Reasons to convert to smart grid. So mainly there are three reasons. The increased energy demand. Now, energy demand is rapidly increased, as I was talking from the beginning, that as the energy demand is rapidly increasing, going to the new technologies, one of them is electric vehicles. Other things are there. And now second, decreasing the losses and illegal uses. The losses and illegal uses in transmission and distribution lines. So now, how to predict the losses and illegal uses? That means, if supposing I have 100 houses and I am supplying to a colony, to a location where there are 100 houses. So now each house has a facility just to give the feedback to the generating company or the distribution.
Yes, sir, we are late because the mic is not working.
Mic?
That's why.
Mic, mic is working.
Recording is on, sir.
So mic is working, na?
Yes, sir. You are fully audible. You are fully audible. Please continue, sir.
No, no, actually I am hearing some voice, mic is not working. So that is why I just retaliated back. Okay, all right. So,
Other participants, please mute.
that is what is happening actually.
Other participants, please. Other participants, please mute.
So then the losses. And
Mr. Saurabh Kumar Singho. Mr. Saurabh Kumar Singho, please mute. Saurabh Kumar Singho, please mute.
Okay. So okay, I'm starting.
Mr. Saurabh Kumar Singho, please mute.
Okay, let it be. So I'm continuing. Huh? So
I request Mr. Saurabh Kumar Singho, please mute. Sir, you please continue, sir.
Okay, okay, I'm continuing. So now the illegal users means if the smart system, they are able to tell you what are the total loads, means one by one, you aggregate it, and then at the input point you measure the power. So if they are tallying, so there is no pilferage, or rather you can say no illegal users. If they are not matching, so you can come to know from which area it is getting tapped. So therefore, I mean, it will be decreasing the chances of illegal uses. Now the
Sir, please mute yourself. I am telling Mr. Saurabh Kumar Singho, please mute your microphone. Mr. Saurabh Kumar Singho, please mute your microphone. Unwanted noises are coming.
Lot of noises.
Mr. Saurabh Kumar Singho, please mute your microphone. Are you audible, Mr. Saurabh Kumar Singho?
Or you can mute from your control point. Mute him. He might not be there.
Sir, you please continue. We will try.
Okay. So the increased production and carriage capacity in the existing plants. Okay. For this reason, actually, a requirement of a smart grid is there. Now we go to the distributed generation system. Now, what are the concepts of distributed generation? Right? Okay. So now in the primitive age, so the generation was centralized, right? When the things began, when the power supply and distribution. Now this center point is actually the center point. Actually, some noise is coming. The center point is actually the generating units.
I would request the participant. Yes, sir. Sorry for the interruption. I would request Saurabh Kumar Singh. Please mute yourself. Hello. Hello. Please mute yourself, Mr. I am finding the name of Saurabh Kumar Singh. Please mute yourself. Sorry for the interruption, sir. One of the participants has unmuted yourself due to which noise was coming. Sorry for the interruption, sir.
No, okay, all right. So I'm continuing, huh? So now there are three types of situations. One is centralized generation, where we have a generating unit here and the load centers are here. Okay. Now from that same generating unit, we are supplying through lines to every load points. So this was earlier. Now then it came decentralized. That means the generating stations became decentralized like this, and they are interconnected, and the local loads are supplied. Now the third one, which is the concept now, which is known as distributed. That means there are small generating units as well as the load units. Now what is the advantage here? Now from the first one, if this one is gone, so all the centers, all the load centers, they're blank. They're blanked. Okay. Now for this one, a little bit better advantage, because say if this one is gone, only this portion is gone, and then the other portions can be actually supplied through other sources. Now for the distributed situation, if any of the source is gone, that means it has some problem, so that there is no interruption to the supply system, because only this is out, and the other lines connected to all these points, they can be able to supply electricity there. So therefore distributed generation is the latest one, and it is the most helpful one, which does not give you any interruption of electric power. So now again, that the beauty of distributed generation is that now earlier we had distribution, transmission, and generation, transmission, and distribution. They are actually by a single company, natural monopoly. So the same company will generate, that will transmit, and that will distribute. Now the problem is that the customer has to actually abide by the rules and regulations, the prices, whatever is there, set up by the single company, and they get suffered also. They have no alternative to change their brand or to change their supply. Now in present, there is an open market. So generation can be from different sources. So we can have 3 or 4 generating companies. Now the transmission also can be 3 or 4 or 5 companies. Now the distribution also can be 3 or 4, 5 companies. Now one customer, they can choose, say, the generation A, transmission B, and distribution C for his or her optimal say power cost, and on the same time other can choose generation B, transmission B, and distribution B. So there are open choices. So now it has become open unbundled market. Okay, so this thing will be actually prevailing in future and will be available later on in order to choose it. Now how to know? Actually the problem is that sitting at your home, you will be able to know which will be less costly, which will be most economic for you. So then in order to do that, you should have a lot of information available to you. So the smart grid system that with some say Internet of Things and all, that will be able to give you all this informations for your choice, right? Now the structure of smart house, you see nowadays, you have added green power sources, you have normal say power line that is also coming, and then the high-speed network connections also should be available, because that will bring you the information. Okay, now the customer interaction utility, smart say plug-in hybrid vehicles, thermostats, and applications in home control devices, and all things will be there. So now this has become a smart house, and it is connected to a grid which is a smart grid. So this grid have all the information regarding your household say electrical activities. Now what are the types of load connected, what is your load cycle, normally when is your peak load, all these things. So that is actually will be helpful later on. Now this is general structure of smart grid. So we have say all renewable sources as well as loads. So nuclear power plant and all, as they are shown, this is a normal picture taken from source. Now normally this is a part of normal power supply unit. Okay, that the line that is coming. Now this is a smart grid. Now if you see the block diagram, if you see the block diagram of your say smart grid system, it has one controller known as distribution management system controller, and this actually is the brain or heart, you can say, of the system that will decide that which to operate when. Like say, supposing you have these sources available: CHP, battery, PV, wind, and these are all connected. At the same time, we have utility supply also, they are coming, right? Now you have loads. So now how to decide that which will be most economical for you? Supposing we have a power supply available from the grid, and it has a cost of say 7 rupee per unit. Now it can calculate also the cost, individual cost. Now if there is a PV, what is your cost? If there is a wind, what is the cost? Now PV and wind, as you have already installed, so when this power will be available, it will not allow any other system to operate, because the other systems that will involve running cost. Okay, now PV and wind, they do not involve any running cost. So when this power is available, this will give a priority. When the other powers, when this is not available, then it will try to fetch from PV. So all these things, all these decisions will be taken care of by this distribution management controller, and you have PQ exchange, everything is available. So now the DG-based architecture with smart grid characteristics offers typical grid. What I was talking, this is explained here. So many type of DGs can indicate various harmonics also, that has to be taken. Now DMSC controller receives measures of signals, also provides control actions, that I was talking. So now then the architecture of DMSC is also like this: the optimal control schedules. So what are the schedules of control? I mean, which at what time what has to be turned on, turned off, like that. So this is there. So now we come to a broader definition of smart grid. So now the broader definition of smart grid means a smart grid uses sensing, embedded processing, and digital communications to enable electricity grid to be now observable. That means it will always can give you a measured frequency, measured voltage, etc. Now controllable, that means manipulated and optimized. Controllable means which load has to be turned off, which load has to be turned off, like that. So these things can be always available. Now automated. Now automated means something like controllability, and again self-healing. Supposing there is a fault in the system, so the circuit breaker will operate and will auto-reclose it after the fault is cleared. That means it has a self-healing property. Now fully integrable, interoperable with existing system, and incorporation of a diverse set of energy sources. That means, as I have already said, that there are 4 types of sources as shown: CHP, battery, and then wind and PV, and even utility. Now it will be integrable with a large number or a wide range of energy sources, and then it can incorporate various types of loads also. So this is the broader definition of smart grid. Now the smart grid should be having following attributes: it enables demand response and demand side management through integration of smart meters, smart appliances, and consumer loads. Now again I'm coming to a small discussion of smart meters. Now smart appliances, consumer loads, micro generators, and electricity storage by providing customers with information related to energy use and prices. Now it should also provide information to customers regarding incentives to modify their consumption. Now this red point you think about, I was talking about shifting of certain loads, right? And I was talking about also regarding peak load times. Right? I was talking about the evening, say 5 to 7 or 5 to 8 p.m. is a peak load time when industries are almost on. Shift operations are always there in almost all the industries. At the same time, light load is on, and in the summertime there are fans also. Now the peak load will appear obviously at the time of evening, and some peak load also appear at the time of say noon also. So then at this time actually there is a lot of pressure on the say existing conventional sources, like say a thermal plant, a hydel plant, a nuclear plant, like that. Now they are designed with some certain plant load factors, so they might not be able to cater with so much of load sometimes when demand increases. Okay, so therefore, if there is a variable tariff system, so that the power supply companies defines that if you consume load during evening time, your energy price will be, say, 15 rupees per unit. Now at the same time, when the load is less, say dawn time, so almost all the ACs are off, say at say dawn, say morning 3 a.m. to say 6 a.m. like that, 3 a.m. to 6 or 3 a.m. to 5 a.m. So when all the air conditioners will be off, lights will be normally off, and the load pattern, I mean, if you see the industrial loads, only the shift work will take place. So therefore, that time the energy price might get reduced. Now, if it gives you an information, if you consume electricity during this time, say 3 a.m. to 6 a.m., your energy price will be 8 rupees per unit. So naturally, some loads that can be shifted. One of them is pump loads that I'm telling. So you can run your pump. Even irrigation pumps also sometimes, so whole day someone may not run, so they can run it during the midnight to the say morning, and have a reduced energy pricing. So then it's therefore the customers should have information regarding incentives to modify their consumption pattern to overcome some of the constraints of the power system. So that will naturally improve the plant load factor and overall cost of the electricity. So that's what now should accommodate and facilitate all renewable energy sources, distributed generation, residential, micro generation, and storage options. So all these things are there. So now I will just quickly come to a place where we go that in order to incorporate this, so then summary is this: optimize power delivery and generation, self-healing, consumer participation, resist attack, that is also talked, high quality of power, accommodate generation options, and an application of digital information technology to optimize the power generation, delivery, and usage. And this will do all these things. Now, then, if you see so this is the basic feature of a smart grid. Now, in order to have technologies, how to incorporate this or how to implement this, now there are the technologies are information and communication technologies that are must actually. Two-way communication technology for connectivity between power system components and loads, right? So I was from the beginning itself I was talking about the communication, information, etc. So in order to achieve this, in order to implement this, so there must be two-way communication. That means the consumer also can bring some information, and it can also provide some information. Then second, open architecture or plug and play and home appliances, electric vehicles, and micro. Open architecture means supposing the loads you connect, suppose you connect a charging system, a battery charging system for your electric vehicle. Now this should be actually a system which itself can give information to the system so that it is connected. So this is taking so much of power, this thing. And it should not happen that this gives you communication in such a mode that will not be received by your say grid system, smart grid system. That means both of them can talk to each other in the platform provided. Okay, so necessarily software and hardware, and necessary software and hardware for greater information trading on energy markets and to provide demand side response of the customers. So these are the technology requirements. Now some softwares should be also there to ensure and maintain the security information and standards to provide scalability and interoperability of the information and communication systems. Okay, so now sensing. Now again, it's, as I was talking about the data fetching and data providing. So in order to do that, there must be some sensing also. Now, which data will say? Supposing I was talking that it has to tell you that a load has been connected with high THD. Now, how does it understand So there must be some sensing, that it senses the harmonics, and then, or it measures the degree of harmonics present, and then it can give you information. And then therefore some technologies should be there for sensing, measurement, and control and automation technologies. The intelligent electronic devices also, and then other things, phasor measuring units and wide area monitoring, protection and control. Phasor measuring units will be required for protecting the system and to ensure security of the power system. So these things should be there, and integrated sensors, measurement and control systems ensure rapid diagnostics and timely response to any events and different parts of power system. Smart appliances, communications and monitors to maximize safety, comfort and convenience, right? And the third one is smart meters, load monitoring and communications. Now, what is a smart meter and what is load monitoring? So this technology, so then in majority, so we land up into the two places. One is the communication, and another is smart appliances and smart meters and load monitoring. So these four things should be there in the smart grid system, right? Now, smart meters actually that will provide real-time information to the customers regarding energy usage. So this is what technology. Now, power electronics and energy usage, this I skip because already some time is lost. Now, this one, non-intrusive load monitoring. So, non-intrusive load monitoring means actually, what is intrusiveness? Intrusiveness means you just go there, open something and see or measure and then tell that this is the thing. Non-intrusive means without opening, without measuring, you just connect your say some sensing unit to the input wire, and then you get to know what are the loads connected, what are the power consumed by each load, what are the individual THD of each loads, what is the active reactive power of each load, that means power factor, all these things. Now this thing will actually tell you, will help the supply companies to understand the nature of loads that are connected and the nature of generations that it should provide so as to give uninterrupted power with high quality. Okay, so then what is NILM? So this is known as non-intrusive load monitoring, NILM. Now a group of techniques are used to obtain estimates of electrical consumption of individual appliances, measurement of voltage and current, limited number of locations of the power distribution systems in a building. Now disaggregating entire electrical loads used in domestic home appliances. So this is what NILM. Now the NILM is not new. It started from 1982 to 1992, and with some load disaggregation for on-off and FSM loads. Okay, finite state machines. That means from this state to that state, on-off and state changing loads, you can say. And preliminarily, a preliminary study of variable load appliances was started in 1992, and in this decade, NILM research was growing slowly. From 2003 to 2020, NILM research is growing exponentially, simply because we are going into more and more automated grid type of system, so that the grid becomes intelligent and it can read the load pattern, it can read the load connected, and it can provide information to the say generating companies also, load monitoring of various appliances. So now what is motivation? Now motivation is that energy saving potential. Smart grid technology, it's a part of smart grid technology. Whenever we try to implement smart grid, so we should go for load monitoring. Otherwise, we'll not be able to understand, we'll be able to implement it. Now, energy saving potential means, again, it can shift you, it can shift your load, it can reduce your consumption, overall consumption sometimes. So it might so happen that you do not need that power. So automatically it will reduce power. Supposing you have automated system where you see that a light, now you have a daylight. Now when you switch on your say your own light, say LED light, whatever it is. Nowadays, of course, light consumption is very less for LEDs, but even then it is there. And then that your CFL and all, And if there is a proper sensing, it can adjust your light generated with your say daylight available. So total light has to be actually sufficient enough for reading. So now it can adjust your load, it can adjust your input so that the total light remains same, and then the consumption is less. So that is why it is energy saving. Now time of use of energy, time of use energy pricing, that I was talking about, shifting of the timing of the loads. So then a non-intrusive appliance load monitor is designed to monitor an electrical circuit that contains number of devices which switch on and off independently. Now by sophisticated analysis, current and voltage waveforms of the total load, and the NALM estimates the number and the nature of the loads, their individual energy consumption, and other relevant statistics such as time of day variation. So these things are there. This I have already talked. No access to the individual components is necessary. That is why it is non-intrusive or installing sensors. Say maybe during the time of installation, it may require some reading or right. Now I go little skipping little some of the talkings. Now here say how to say identify rather. Now the NALM monitors, the NALM monitors the total load, checking certain signatures which provide information about the activity of the appliances which constitute the load. So these points should be remembered. Now how NALM is implemented? Supposing you have a refrigerator. Now a refrigerator has got certain patterns. So it may go to some frost mode, some normal mode, and both these times there is some active reactive power consumption pattern. So now each load has some signatures, like a fan. A fan has some signatures, say active reactive power only. Forget about your current pattern, etc., etc. So initially, I mean, all these techniques were not available to have a very fast computing facilities, like they can have some input current data and go for fast Fourier transform with high computational ability, with processors having high computational abilities. And then they started with some crude signatures, like say active reactive power. Now that will give you a pattern of load. So this will work with the signatures which provide the information about activity of the appliances which constitute the load. Sometimes say the fridge, refrigerator, so defrosting, normal, like that. Now this is an example. If a residence contains a refrigerator which consumes 250 watt and 200 bar, then a step increase of that characteristic size indicates that the refrigerator is turned on, and a decrease of the size indicates turn off of the events. Other appliances have other characteristic signatures like this. So after determining the exact on and off times from the signature events, so any desired statistics, suppose I study your home, say what is the pattern, 10 days, 15 days, months, 1 month. So then I can get to know this is your load pattern for Sunday, this is your load pattern for Monday, like that. Yeah, so that can be helpful for the generating companies. Now that can be tabulated also. So now I'll just show you a pattern. So this is a typical load cycle. So then electric power, so this is the refrigerator cycle, this is turn on and this is turn off. This is a 2-hour cycle, and this is turn off, and again refrigerator, and with the refrigerator there are some, say, heater, 6 heater cycles. Now refrigerator off, there are heaters. So and then refrigerator. So then if I study the on and off pattern, now looking at this, I can tell refrigerator is on. Now here every load is off. Now here refrigerator on, again on and off pattern, so I can say this is a heater. This is a characteristic of the heater. So then looking at your cycle, so I can come to know what are the loads that are connected in your home. Then there is another 40-minute cycle. This is a refrigerator cycle. Refrigerator has got some normal operation, frosting and all. So this, and then some oven, then some stove burner, and then that is off. And again refrigerator, and with some, say, this is another stove burner, oven element. So these things, this pattern can be studied say over some 1 month or 7 days like that, and then based on which I can predict, or the smart system can predict what is the load, what is the pattern of the load connected to your system. So this is what. Now the NLM approach reverses this balance with simple hardware, complex. Now actually, now the traditional load research instrumentation. Now the traditional research actually involves complex data gathering hardware but simple software. Now normally what happens, I was talking that how to do it. Now you have complex data gathering means you should note the current, you should note the voltage, you should go for the first Fourier transform, you should go for harmonics, fundamental components, etc., etc. That means the data gathering and data collection is really complex, right? But the decision making software, that means from that data, if third harmonic there, yes, this load. If fundamental is this much, so this load. So this is simple. So now the traditional research is actually the complexity in instrumentation and easiness in the implementation software. But the NLM approach reverses this balance. Now, how to do it? Now, it should have simple hardware. I was just telling you that at the input of the system, we just monitor some voltage and current. That's all. Now we want to know that what are the loads connected, what are the this. That means we should have some complex software for signal processing and analysis, right? Now the NLM actually will reverse this, and then it will have simple sensing but complex computation. So it requires high-end processors. It is possible simply because with the advent of say cheap at lower the high computational ability processors, high quality processors at cheaper cost. Now you will know how to use Raspberry Pi and other ATmega processors and all. Now they are very simple to operate. At the same time, they have good computational ability to do this kind of actions. So you are, I think, even the students, first year students, they are able to have some communications with Raspberry Pi, and then they have some Internet of Things actions, and then control from the say, Android and all these things. So these are easy to operate. Now again, I will remove some of the talkings. Now this thing again comes the the NLM goals. If you see non-intrusiveness, actually the NLM goals, there are two types. There's manual setup, another is an automatic setup. Now what is manual setup? Now in manual setup is a non-intrusive behavior tracker which requires one-time intrusive period of the setup. During the intrusive setup, that means manual setup means, okay, I come to your home, so I collect data from each of the loads. Suppose refrigerator, so I will tell you, you just switch on, switch off refrigerator, I record the thing. I record the thing. Then again, television. So I will tell you, switch off all the loads, only turn on television, you just switch on, switch off, and I will record the pattern. So this way, manually I store each characteristics, right? And then I store the data and program it into your system, and then tell that this is the pattern whenever you are turning on, turn off any device. Then second one is that automatic setup. Now in this automatic setup, the system has got some a priori knowledge about your load. Supposing you tell me I have these loads. So then once you tell me you have these loads, so I have already some a priori knowledge based on the say known things, and then I embed this into my controller, and then whenever you switch on, switch off, or do something in your home, I can just predict or tell you or tell the system that this is the thing what is happening. So this ASNLM sets itself as it measures the load using a priori information about the characteristics of the possible appliances. It must determine the important signatures and the appliances will which they are associated without the benefit of any entry or appliance survey. So nothing is required. Okay, it automatically it takes up. Now the MS-NALM has been a stepping stone in the development of AS-NALM, right? Like and will likely serve as the analyzing tool situations where AS-NALM fails. Okay, so then I go. I think I am running out of time, but within the next 5 minutes I complete. So I will show some of the this pattern. So actually, this is one signature space, right? Now signature space, I was telling about load signatures. Now the load signatures are that whenever there is a load is switched on, it has some characteristics apart from the current and voltage and all. There is some crude characteristics like the power, input power, reactive power. So this is known as clusterification. Now clusterification means, if you see that it is a water pump, that means normally this is the active power, this is the reactive power. So if I plot active versus reactive versus active power, so I get some clusters like this: humidifier, this ice maker, this is vent fan, this is IR light, this is refrigerator, this is bathroom light. So then you see that this is electric iron. That means whenever it falls in this cluster, it is some sort of heating loads. Whenever it falls in this cluster, there is some motors, right? Motors with higher power. Now this is also motors, but this has got lower reactive power. Okay. Now this is light load. Light load means reactive power is 0. Reactive power is 0 almost. So then from this cluster, people try to study the load pattern and give information to the customers. So now again, I skip these things. So I will go to we have also done some work on that. So I think time will not permit. Within the next 5 minutes, I have to find. So now I will show you role of IoT. Now the role of IoT. So one of the most important service of smart load management is residential appliance monitoring. That we have already seen from the past 1 hour, say 1 hour or 1 hour 15 minutes of lecture. Now then, if it is so that smart load management, so that will involve certain information. So load monitoring unveils different types of electrical loads as motoring load, power electronic load, lighting load, and so on. So nowadays, development in the recent technology, for example, Internet of Things, Internet of Things communications allows extension of smart energy networks in a smart house. That means along with smart meters. Why I am telling that if you look at a smart meter nowadays, I think some of your speakers will be giving you a little more insight, because I had no time regarding that of smart meters. So if you see that till now, the smart meters have got a limited range of actions, like it can only tell you active, reactive power, connected, total load, this thing, that thing, etc. But this will not be able to tell you that the total amount of harmonics that is injected by this load, harmonics injected by that load, active reactive disaggregation, that means total load, total active reactive power it can tell. But from the at the entry point, say supposing you have fan, refrigerator, and then a pump, and then some light is connected, and at the entry point you will be able to switch on, you will be able to know that which load is taking how much active power, how much reactive power, what is the fundamental component of current, what is the fundamental power, what is the harmonic power. So all these things, facilities are not there. So therefore this IoT actually will be able to make up some of the shortcomings of the smart meters. Okay, so then this is why I have said that it will be actually operating at tandem, rather with us, along with smart meters. Okay, it will have some additional things which the smart meters do not have. The IoT can have an extremely crucial role in the control of smart grids and smart cities. Under conventional smart meter, total energy consumption information is continuously monitored and sent to the utility for the other services. That I have just told you. So no such meter is available in the market for information of each load or load disaggregated. Loads are switched on and off, which remotely communicates utility and customer. That's what I was talking, that it can tell you about the total things till date. But there is the technology is not there which can tell you that this is the individual load pattern, this is the individual energy consumption, individual power, individual harmonics, individual THD, etc. So therefore, to mitigate this problem, IoT-based residential load monitoring offers a suitable solution. So those who are actually seeking some research topics, I think this is a very good opportunity. So this area where they can do something, where they can actually integrate with smart meter and give some additional information with the help of IoT, and then give you a total package, so that both the supply companies as well as the consumers, they are benefited. Okay. Now the IoT platform has two layers: physical layers, which includes the hardware, for example, sensors, networking gears, etc. And the second layer is the network layer, which transmits data from physical layer to different other devices. Besides this, for remote application, a dashboard and all these things. So I'm just closing here. Now it has got message queue telemetry transport system protocols. Now this is MQTT block diagram, so it can actually have some broker, which is the consumer, and then it can communicate with the subscribers. Okay, and then subscribers, and we have a database and along with sensors and all. So my conclusion is that in future, with the smart grid, which is actually connected with some say normal conventional grid system as well as the renewable sources, will be coming in future to a large extent, in order to reduce the different disadvantages that I have already talked about. And with the smart grid, we should have invariably smart meters along with IoT technology to compensate for that, because if we try to incorporate everything in smart meters, the cost of the smart meters will be beyond the reach of the normal people, and it will not be an easy thing to implement. Now, if we have some optional features with IoTs and all, along with the smart meters and in the smart grid system, so this will actually give the ample opportunity for the consumers and as well as the generating companies also to work in a structured pattern, and to provide the customer with, say, more reliable, secure power with high power quality, and for the critical loads also. So thank you very much. I think there were some disruptions. I'm sorry for that because of some technical drawbacks. So I think I tried to explain, but if you have any questions, please come forward, so I will try to answer your queries.
Sir, first of all, very good afternoon to you. Very good afternoon.
Thank you.
Thank you. It was a very much informative session, and you have shown lots of lights on various topics on smart grid, such as distributed generation, security, reliability, smart grid, distribution, regulation, control techniques, unburdened market, information, IoT, distribution management system, controller, NALM, MOTT, smart load management. Sir, I am deciding speaking. I am also working on this area. I am very much privileged that you have again come to our institute and given such a highlights to the smart grid technology and IoT and all these things. It is a very much. We are very much privileged to you, sir.
Thank you. So
one question there. One question is there from the audience. Can we store data in cloud through IoT of daily energy consumption?
Definitely we can store data. When we have actually implemented the NALM technique, and then from that we can fetch data through IoT and store. Definitely.
Yes. Okay, sir. So
So
then
actually,
any participant.
we have done some work also on it. I mean, I could not show you because of shortage of time. So we have implemented some NLM technique also with some intelligent method, and then this IoT technique is also getting introduced in it. So I mean, I will request. So if anyone, they can also start. I mean, you can say budding area, and in future you will find lot of research papers. They are coming in this area, and that will be helping to implement the smart grid system in a say large broader fashion.
Okay, sir. Very much thank you. Any more questions from the participants? Any more questions from the participants?
Participants are requested to ask the question to sir directly. You may ask. I think there is no more questions.
Okay, because it's really theoretical. And
Sir, I will request Mr. Akendo Mitro to present you a memento certificate to you, sir.
Sir, on behalf of the department, I am presenting. But first of all, you have to stop your presentation, please, sir.
Okay. Stop the presentation.
Thank you, sir.
Okay, I am
then
going
I'm
for
able
the.
to show you the token of appreciation, the certificate.
Okay.
Sir, is it
Thank you very
visible?
much. It is visible. Thank you very much.
Okay, sir. We will mail you, sir.
Okay.
Okay.
So I would expect that few of you at least will be in, this as a result of this good discussion, not by me. There will be many speakers, so you can actually align yourself, at least one or two or few of you that can help your. These days power system has shifted to this area. Actually, you don't find big good equations, good conventional, you can say classical power system papers that are coming. There are very few, but mostly they are shifted towards this kind of things. But okay, this is the modern things that is coming, so that you have to also cope up with this. Okay.
Okay, sir. Very much thank you. You have shown a great light on this smart grid, and we are very much privileged to you for giving such a nice talk.
Okay. Thank you very much.
Okay, sir. Thank you.
Thank you,
so
sir.
I am exit.
Yes, sir. No problem.
Okay, you were trying to say something.
No, sir.
Okay.
No.
Thank you.
I'm going to close the session.
Okay. Thank you. So I am leaving. Yeah.
Okay. Thank you, sir. Thank you.
Okay, sir. Okay.
All right.
Then we'll meet again tomorrow 10 a.m. sharp. Please, I'm leaving.
Okay, sir. Okay.